Somewhere, far beyond the reach of our most powerful telescopes, a lone star pulses in the darkness, not with the rhythm of fusion, but with the heartbeat of a cosmic secret. Deep within its core lies something impossible, a stable wormhole, a bridge between worlds, perhaps even between universes. To any passing traveler, it might seem like just another star in an endless sky. But step too close, and you could be pulled through a gateway to places where the laws of physics are rewritten, where time folds in on itself, and where no human has ever returned. This is the Wormhole Core Star, a phenomenon that could hold the key to infinite exploration, or unimaginable danger. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Now, picture the vast stretches of the cosmos. For decades, we've known stars as the fundamental building blocks of galaxies, engines of nuclear fusion, forging elements in their fiery hearts, illuminating the dark void. Yet, the idea that some stars might also serve as doorways, bridging vast distances instantly or even connecting entirely different universes, adds an entirely new dimension to our cosmic understanding. These are no ordinary stars. They are stars whose cores contain stable wormholes, hypothetical tunnels through space-time that could allow matter, information, or even entire starships to traverse incredible distances instantly. Wormhole core stars represent the intersection of astrophysics and speculative science, a frontier where the boundaries between the known universe and the unknown blur. The implications are staggering. If such stars exist, they could explain some of the universe's deepest mysteries, offer insights into multiverse theory, and potentially revolutionize space travel forever. The concept is rooted in advanced theoretical physics and general relativity, blending the exotic ideas of wormholes with the well-understood phenomena of stellar evolution. While most wormholes predicted by physics are unstable and collapse almost instantly, a wormhole core star is theorized to somehow naturally maintain a stable wormhole inside its fiery center. This stability is key. It turns a theoretical tunnel into a potentially traversable passage. So what exactly is a wormhole core star? It is a star whose core doesn't simply burn hydrogen and helium but somehow harbors a stable wormhole, a tunnel connecting 2 points in spacetime, which could be light years apart, or in entirely separate universes. This star would look much like any other from a distance but would possess unique gravitational and radiative properties hinting at the extraordinary phenomena inside. Why is this idea so compelling? Because it suggests that nature itself might have found a way to create shortcuts through the cosmic web, pathways that could challenge our concepts of distance, time, and space travel. A wormhole core star could be the ultimate cosmic gateway, a living portal in the vast darkness. Such stars have not been definitively observed yet, but scientists are actively searching for indirect clues, unusual light patterns, gravitational anomalies, or unexplained cosmic signals. The discovery of one would revolutionize physics and cosmology, confirming wormholes as physical objects rather than just mathematical curiosities. In this video, we will embark on an extraordinary journey, exploring every aspect of these potential cosmic gateways, from the physics of wormholes themselves, to the exotic matter required to stabilize them, to the possible destinations through their tunnels. We will speculate on the risks and rewards of traveling through such stars, consider their role in cosmic mysteries like fast radio bursts, and ponder the profound ethical questions they raise. This is not just about stars. It's about unlocking the secrets of the universe and perhaps other universes entirely. To understand wormhole core stars, we first need to grasp what a wormhole itself actually is. At its essence, a wormhole is a theoretical passage, a tunnel, through the very fabric of spacetime. Imagine spacetime as a two-dimensional sheet, like a piece of paper. Normally, to get from one point on that sheet to another, you would have to travel across the surface. But if you fold that sheet so that two distant points touch, and then pierce a hole through both, you create a shortcut, a wormhole, allowing you to travel between those 2 points instantly, bypassing the vast space in between. In the world of physics, this shortcut isn't just a fun thought experiment, it's a mathematical solution that arises from Einstein's theory of general relativity. Wormholes are sometimes called Einstein-Rosen bridges, named after the physicists who first described them in the 1930s. They represent hypothetical tunnels through space-time connecting two separate regions. These regions could be different places in our universe, perhaps light years apart, or even entirely separate universes within a multiverse. What makes wormholes so fascinating is their potential to revolutionize how we think about distance and time. Instead of traveling for thousands or millions of years to reach a distant star, a spaceship passing through a wormhole could theoretically arrive instantaneously or at least much faster than light traveling through normal space. But wormholes come with many caveats. According to standard physics, traversable wormholes, those that could safely allow matter to pass through, require exotic conditions, like the existence of exotic matter that behaves unlike anything we've observed in everyday life. Most solutions to the equation show that wormholes would collapse immediately upon forming, snapping shut before anything could cross through. Yet, if somehow a wormhole could be kept open and stable, it would provide a cosmic shortcut across the universe, and possibly even between universes, a tantalizing concept that captures the imagination of scientists, sci-fi writers, and curious minds alike. This theoretical tunnel is more than a simple spatial shortcut. Because of how space-time is linked with time itself, wormholes might allow for shortcuts not only across space but also potentially through time. The idea that they could connect different points in time as well as space opens the door to possibilities like time travel, causality paradoxes, and other mind-bending scenarios. Scientists visualize wormholes as two mouths connected by a throat, the tunnel, through which something could pass. The size and stability of this throat depend on complex interactions involving gravity and exotic forms of matter or energy. Most known wormholes would be microscopic and unstable, vanishing in an instant, but the hypothetical Wormhole Core Star challenges this by potentially housing a naturally stable, macroscopic wormhole large enough to influence stellar dynamics. Wormholes, while still theoretical, are one of the most exciting predictions of modern physics. They offer a glimpse into a universe far stranger and more interconnected than the smooth, predictable cosmos we observe daily. Whether as shortcuts across the stars or bridges to other universes, wormholes stretch the imagination and scientific curiosity to their limits. Wormholes are not just imaginative ideas. They actually arise from the very fabric of Einstein's general relativity equations. When Einstein formulated his theory, he described gravity not as a force, but as the bending and warping of spacetime caused by mass and energy. Massive objects like stars and planets curve the spacetime around them, influencing the paths that objects take. Mathematically, the equations Einstein developed, known as the Einstein field equations, are highly complex and allow for solutions that describe a variety of spacetime geometries. Among these solutions, in the early 1930s, physicists Albert Einstein and Nathan Rosen discovered what is now called the Einstein-Rosen bridge. This bridge was essentially a tunnel-like connection between two different points in spacetime, which we today call a wormhole. This solution emerged when they tried to describe a particle as a bridge connecting two separate sheets of spacetime. The math showed that spacetime could be folded in such a way that two separate locations could be linked through this bridge. However, their initial model described a wormhole that was non-traversable, meaning it would pinch off too quickly for anything to pass through. Later, scientists including Kip Thorne and others expanded on these ideas to explore traversable wormholes. Wormholes that remain open long enough to allow matter or information to cross. To achieve this, the mathematics indicated the need for exotic forms of matter with unusual properties, such as negative energy density, to stabilize the wormhole's throat and prevent collapse. So, wormholes aren't just sci-fi dreams. They are valid, albeit highly theoretical, solutions within Einstein's equations. They reveal that spacetime might be far more flexible and interconnected than we perceive, capable of creating tunnels or shortcuts that link distant corners of the universe, or even different universes, if the right conditions exist. Wormholes, as intriguing as they are, face a fundamental problem: stability. The majority of theoretical wormholes that arise from Einstein's equations are incredibly fragile. They collapse almost instantly, closing off any passage before even a photon could pass through. Understanding why this happens is essential to appreciating why a stable wormhole is such a rare and extraordinary phenomenon. At the heart of this instability is the way gravity and spacetime interact. Gravity tends to pull matter and energy inward, compressing anything that distorts spacetime. When a wormhole forms, it creates a tunnel connecting two regions of spacetime, but this tunnel is naturally prone to collapse because the intense gravitational pull around the throat of the wormhole wants to pinch it shut. Think of it like blowing a bubble between 2 points. Without some form of reinforcement, the bubble quickly bursts under pressure. From the mathematical perspective, wormholes require what physicists call exotic matter to remain open. Exotic matter is theorized to have negative energy density or negative pressure, qualities that are not observed in normal matter. Negative energy essentially pushes outward, counteracting the inward pull of gravity that would otherwise close the wormhole. Without this outward push, the throat of the wormhole collapses immediately after forming. This concept of negative energy may sound abstract, but it does have some roots in quantum physics. Phenomena like the Casimir effect show that negative energy densities can exist, at least temporarily, on very small scales. However, scaling this up to the level needed to stabilize a macroscopic wormhole remains purely speculative. Creating or finding enough exotic matter to hold open a wormhole large enough for a star or spaceship to pass through is beyond any current scientific capability. Because of this, most wormholes modeled in theoretical physics are non-traversable. They exist mathematically but cannot be used for travel or communication. They might appear and disappear so rapidly that they cannot be exploited, or the tidal forces inside them would be so extreme that anything attempting to cross would be destroyed. A stable wormhole, then, is a wormhole that somehow manages to avoid this collapse and remain open for extended periods. This stability could be maintained by an unusual concentration of exotic matter or through unknown quantum gravitational effects that counterbalance the forces pulling the wormhole closed. Why is this so rare? First, the conditions needed to produce and sustain the exotic matter or energy are extraordinary and currently unconfirmed. Second, maintaining a wormhole's throat open against the relentless pull of gravity requires a precise balance. Any slight perturbation could trigger collapse. The energy conditions that must be violated to keep a wormhole open do not align with the normal behavior of matter and energy we observe throughout the cosmos. Some theoretical models propose that quantum effects, such as those predicted by theories of quantum gravity, might naturally stabilize certain wormholes. In these models, the vacuum fluctuations of spacetime at the quantum level generate enough negative energy to hold the wormhole open. This idea remains speculative but tantalizing because it hints that nature might have found a way to create stable wormholes without human intervention. Another line of thought involves hypothetical particles or fields, like those associated with dark energy or exotic states of matter, that could exist inside certain extreme cosmic environments. If such substances could concentrate naturally inside a star's core, they might provide the necessary negative pressure to stabilize a wormhole. In this context, a wormhole core star becomes a fascinating possibility. Unlike typical wormholes that require artificially engineered exotic matter, this type of star could naturally generate and maintain a stable wormhole through its unique internal conditions. The intense gravitational forces, extreme densities, and perhaps exotic phases of matter deep inside the star's core might combine to produce the precise environment needed for stability. This raises profound questions. Could the universe itself have forged stable wormholes inside certain stars as a natural process? Could these stars serve as cosmic gateways or shortcuts without any intelligent design? The rarity of such objects would explain why we have not yet definitively observed them, but their existence would open a new chapter in astrophysics and cosmology. The rarity of stable wormholes also stems from the fact that their existence challenges many classical energy conditions in physics, rules that govern how matter and energy behave. Violating these energy conditions leads to exotic scenarios that strain our current understanding. For example, the null energy condition, a fundamental assumption in general relativity, must be broken to sustain a traversable wormhole. Because this is so unusual, scientists remain cautious but curious about the possibility. Finally, even if a stable wormhole forms, its long-term survivability would depend on its environment. Interactions with surrounding matter, radiation, and gravitational waves could destabilize it. Only under very special circumstances, perhaps inside a uniquely composed star, could it remain open long enough to have significant cosmic effects. Thus, a stable wormhole is like a cosmic unicorn, theoretically possible but extraordinarily rare, requiring conditions that push the boundaries of physics. Understanding how one might form and persist is at the frontier of research, and wormhole core stars represent one of the most captivating ideas bridging these extremes. A wormhole core star stands apart from ordinary stars in a fundamental and extraordinary way. It harbors a naturally occurring, stable wormhole right at its center. This characteristic sets it apart not only in its internal structure but also in its cosmic role. Unlike typical stars, which are powered by nuclear fusion processes in their cores, wormhole core stars possess a core environment so extreme and unique that it can sustain a tunnel through space-time, a wormhole, that remains open and stable over time. To appreciate what makes a wormhole core star different, we must first consider what happens inside a normal star. A typical star, like our Sun, generates energy through nuclear fusion. Hydrogen atoms collide and fuse to form helium, releasing immense amounts of energy in the process. This energy creates outward pressure, balancing the inward pull of gravity and maintaining the star's structure in a state of equilibrium. The core is intensely hot and dense, but its makeup is still composed of ordinary matter, protons, neutrons, electrons, behaving according to the familiar laws of physics. Now, imagine a star whose core is fundamentally altered by the presence of exotic matter or quantum phenomena capable of stabilizing a wormhole. Instead of being solely a fusion furnace, the core of a wormhole core star becomes a complex and dynamic region where the usual rules bend. The intense gravitational compression at the center, combined with the presence of exotic forms of matter, perhaps negative energy densities or quantum vacuum effects, allows a tunnel through space-time to form and remain open. This stable wormhole at the core creates a radically different internal geometry. While normal stars curve space-time around them in a relatively predictable way, wormhole core stars warp space-time more dramatically, generating a throat or tunnel that connects disparate points in space or possibly even different universes. The star's core is not just a dense ball of plasma. It is effectively the mouth of a cosmic passage. One key factor differentiating wormhole core stars is how their internal pressure and density profiles are altered by the wormhole's presence. The exotic matter and the wormhole's geometry provide an outward pressure that counteracts the gravitational collapse that would normally cause the star's core to contract or collapse into a black hole. This unique balance stabilizes both the wormhole and the star, enabling the star to exist in a state unlike anything seen in conventional astrophysics. Moreover, the formation of the wormhole alters how energy and matter behave within the star. Some theoretical models suggest that matter falling into the core could be channeled through the wormhole tunnel to a different location, effectively making the star a cosmic conduit rather than just a luminous object. This idea challenges traditional notions of stellar behavior, potentially explaining unusual observational phenomena like strange light emissions or gravitational anomalies. Unlike black holes, where matter collapses into a singularity hidden behind an event horizon, wormhole core stars avoid the formation of such a singularity at their centers. Instead, the wormhole throat acts as a bridge that prevents the formation of an event horizon and singularity by redirecting matter and energy through the tunnel. This crucial difference means wormhole core stars do not trap everything inside but instead maintain a dynamic connection with another region of spacetime. In essence, what makes a wormhole core star different is the natural, sustained formation of a wormhole within its core that reshapes its internal structure, behavior, and interaction with the surrounding universe. It is a star that is both a stellar object and a cosmic gateway, a dual nature that challenges and expands our understanding of what stars can be. This extraordinary nature means wormhole core stars would possess unique gravitational fields, radiation signatures, and perhaps even magnetic effects, setting them apart from ordinary stars and making them detectable, at least in principle, through careful astronomical observation. The formation of a wormhole core star is a subject that blends the cutting edges of astrophysics, quantum mechanics, and speculative theoretical physics. Unlike normal stars, whose birth and life cycle are governed by well-established processes, gravitational collapse of gas clouds, nuclear fusion igniting in their cores, and a balance between radiation pressure and gravity, the birth of a wormhole core star would require conditions far more exotic and unusual. At the heart of this question is what physical processes or cosmic circumstances could produce the extreme environment necessary for a stable wormhole to form and persist inside a star's core. Theoretical physicists have proposed several intriguing possibilities, though it's important to stress that all remain speculative, awaiting either observational evidence or a fuller theory of quantum gravity. One possible pathway to the formation of a wormhole core star involves the collapse of an unusually massive and dense stellar object. When massive stars exhaust their nuclear fuel, their cores collapse under gravity, typically forming neutron stars or black holes depending on the mass. However, if the collapsing core contains or generates exotic matter, a hypothetical form of matter with negative energy density, it might prevent total collapse into a black hole. Instead, the exotic matter could create the conditions for a wormhole throat to open in the heart of the star. The presence of exotic matter inside the collapsing core would be critical. Exotic matter's unusual properties can counteract gravity's crushing force by producing negative pressure. This negative pressure would act as an outward push, balancing the inward pull of gravity and preventing the singularity that normally forms at the center of black holes. In this delicate balance, a stable wormhole could theoretically form and remain open within the star's core. Another theoretical scenario invokes the role of quantum effects in extremely dense matter. As the density and gravitational forces inside a collapsing star's core reach near Planckian scales, the incredibly small scales where quantum gravitational effects become significant, the classical picture of gravity breaks down. Quantum gravity, an area still under intense research, may allow for the spontaneous formation of wormholes through fluctuations in spacetime geometry. These quantum fluctuations could stabilize a tunnel-like structure inside the core, effectively creating a natural wormhole. Certain quantum gravity approaches, such as loop quantum gravity or string theory, hint that spacetime at the smallest scales is not smooth but granular and dynamic. In such a context, wormholes might be stable features emerging from the complex quantum foam that underlies spacetime. A collapsing star reaching these densities might trap one of these quantum wormholes in its core, anchoring it in place and allowing it to grow or persist as the star evolves. In addition to quantum effects and exotic matter, the formation of a wormhole core star could depend on the star's initial conditions during its birth from a molecular cloud. For instance, stars forming in regions with intense magnetic fields, unusually high concentrations of dark matter, or strange energy fields might develop cores with exotic properties conducive to wormhole formation. Some models speculate that regions of the early universe with high energy densities could have seeded such exotic stars. Another fascinating angle considers the potential influence of dark energy, or dark matter. These mysterious components make up about 95% of the total mass energy content of the universe, yet their nature remains elusive. If dark matter or dark energy can interact with baryonic matter the normal matter stars are made of, under extreme conditions, they might contribute to stabilizing exotic structures like wormholes inside stars. For example, a dense core enriched with dark matter particles or affected by dark energy pressure might sustain the negative energy densities required. Theoretical studies have also explored whether accretion of exotic particles or cosmic strings, hypothetical one-dimensional defects in spacetime predicted by some grand unified theories, could catalyze wormhole formation inside stars. If a star captured such an exotic object in its core, the intense gravitational environment might twist spacetime enough to create a tunnel. The time scales involved in forming a wormhole core star could vary widely depending on these processes. Some models suggest that a wormhole could form during the late stages of a star's life, perhaps during supernova collapse, while others propose primordial origins, where such stars formed directly from exotic matter in the early universe and have survived since. Importantly, the formation of a wormhole core star would require conditions not just to create a wormhole, but to sustain it against collapse or evaporation over cosmic timescales. This sustained stability implies a continuous supply or presence of exotic matter or stabilizing quantum effects, making these stars incredibly rare and difficult to detect. Theoretical modeling and simulations are beginning to explore these ideas, though the extreme physics involved pushes current computational limits. Understanding how such stars could form and evolve remains one of the most challenging frontiers in theoretical astrophysics. If wormhole core stars do form naturally, their discovery would provide unprecedented insight into the fabric of spacetime, the nature of exotic matter, and the interplay between gravity and quantum physics at stellar scales. The stability of wormholes, a concept that captivates both physicists and science fiction enthusiasts, hinges fundamentally on the presence of what is known as exotic matter or negative energy. These are not just abstract terms, they represent some of the most profound and puzzling ideas in modern theoretical physics. To understand how a wormhole might remain open, especially within the core of a star, we must delve deeply into the intricate physics that govern spacetime, energy, and gravity. At the root of the problem is gravity itself. Gravity, as described by Einstein's general relativity, is an attractive force that pulls matter inward. In the case of a wormhole, which can be visualized as a tunnel connecting two distinct points in spacetime, the immense gravitational forces near the wormhole's throat tend to pinch the tunnel shut, making it unstable and non-traversable. To counteract this natural tendency of collapse, the presence of a form of matter or energy that exerts repulsive gravitational effects is required. This is where exotic matter and negative energy come into play. Exotic matter is defined as any matter that violates the classical energy conditions of general relativity, particularly the null energy condition, NEC. The NEC, in simplified terms, states that for any light-like vector, the energy-momentum tensor contracted twice with this vector must be non-negative. Physically, this condition implies that energy density, as measured by any observer, should not be negative. Ordinary matter, such as the particles making up stars and planets, satisfies these energy conditions. However, for a wormhole throat to remain open, the NEC must be violated, which requires matter with negative energy density, exotic matter. Negative energy is an exotic concept, but it has some grounding in quantum physics. One of the most famous manifestations is the Casimir effect, where two very close, uncharged metal plates placed in a vacuum experience an attractive force because the vacuum energy density between the plates is lower than outside, effectively creating a region of negative energy density. Although this effect is minuscule and occurs at microscopic scales, it demonstrates that negative energy can exist, at least in principle. In the context of a wormhole, the negative energy, or exotic matter, would produce a repulsive gravitational field, effectively pushing outward on the wormhole's throat and balancing the inward pull of gravity. This delicate balance keeps the wormhole stable and prevents it from collapsing. Without such exotic matter, the wormhole would pinch off in an instant, making it useless as a bridge through spacetime. Within the extreme environment of a wormhole core star, it is theorized that conditions could naturally foster the presence of exotic matter or negative energy densities. The incredibly high densities, intense gravitational fields, and possibly unique quantum states in the stellar core might create or trap exotic forms of matter. For example, vacuum fluctuations in the quantum fields could be amplified by the star's gravity, sustaining a region where negative energy density exists in sufficient amounts to stabilize the wormhole. Another theoretical mechanism involves quantum inequalities and the distribution of energy in curved spacetime. Certain quantum field theories predict that negative energy can be sustained temporarily in specific configurations, and the dynamic environment inside a star's core might allow these configurations to persist longer or be replenished continuously. Theoretical physicists have modeled wormholes stabilized by various types of exotic matter, including phantom energy, a hypothetical form of dark energy with even more unusual properties than the dark energy driving the universe's accelerated expansion. Phantom energy would have a strongly negative pressure, which could exert enough repulsive force to keep a wormhole throat open. Additionally, some models incorporate scalar fields, fields represented by a single value at every point in space and time, that could exhibit negative energy densities under certain conditions. These scalar fields might exist naturally in the universe or be generated through interactions in the dense stellar environment. Crucially, the quantity and distribution of exotic matter must be just right. Too little, and the wormhole collapses. Too much or unevenly distributed, and the structure becomes unstable or develops singularities. Theoretical studies often explore thin shell wormholes, where the exotic matter is concentrated in a thin region around the throat, minimizing the amount needed and possibly making stability more achievable. One of the challenges in this field is that exotic matter and negative energy remain largely theoretical constructs. We have no confirmed observations of macroscopic exotic matter, nor do we understand fully how to create or maintain it in large quantities. The exotic matter required for stable wormholes also tends to violate causality or lead to paradoxes, raising questions about whether such configurations can exist in our universe. Nevertheless, the concept that a star's core might naturally accumulate or generate the exotic matter necessary to stabilize a wormhole is a profound and compelling hypothesis. It suggests that the universe could harbor astrophysical objects far stranger than black holes or neutron stars, where quantum physics and gravity intertwine in unexpected ways. If such exotic matter exists in these stars, it would fundamentally alter the star's internal dynamics, possibly affecting its radiation, gravitational field, and evolution. This makes wormhole core stars not only theoretical curiosities but also potentially observable phenomena, given the right instruments and detection methods. In sum, the theoretical physics behind wormhole stability centers on the existence and properties of exotic matter or negative energy. This extraordinary form of matter acts as the essential scaffolding that keeps a wormhole open, counteracting gravity's collapse and enabling the possibility of a stable tunnel through space-time. Within a wormhole core star, the interplay of extreme density, gravity, quantum effects, and exotic matter could create and sustain this delicate balance, making the star both a celestial body and a cosmic gateway. The question of whether wormhole core stars are real, actual, physical objects inhabiting our universe remains one of the most tantalizing and challenging in modern astrophysics. Because these stars would be fundamentally unlike any conventional star, detecting them directly is difficult. They might not reveal themselves through the familiar signals of ordinary stars, and their defining characteristic, the stable wormhole in their core, is invisible to traditional telescopes. As a result, scientists focus on searching for indirect evidence, subtle clues hidden within the cosmos that might betray the presence of such extraordinary objects. One of the primary ways researchers seek evidence of wormhole core stars is through careful analysis of unusual gravitational effects. Since these stars contain a stable wormhole, a dramatic warping of spacetime at their centers, they are expected to exhibit gravitational signatures that deviate from those of typical stars or even black holes. For example, the gravitational lensing caused by a wormhole core star could differ in distinctive ways, bending light from background objects differently or producing multiple images with unusual properties. Detecting such anomalous lensing effects is a major focus of observational campaigns using space telescopes and ground-based observatories. Moreover, wormhole core stars might generate unique patterns of radiation. Stars generally emit light across a broad spectrum based on their temperature and composition, but a wormhole core star could display irregular or unexplained spectral lines. These might stem from exotic processes occurring near the wormhole throat, such as matter being accelerated or channeled through the wormhole, or from exotic particles interacting in ways not yet understood. Astrophysicists analyze data from X-ray, gamma-ray, and radio telescopes looking for anomalies that don't fit established models of stellar behavior. Fast radio bursts, FRBs, mysterious and powerful pulses of radio waves detected from distant galaxies, have sparked particular interest in this context. While their origins remain uncertain, some researchers speculate that wormhole core stars could be natural candidates for FRB sources. The idea is that processes near or inside a wormhole throat might produce sudden bursts of energy, sending radio pulses across the cosmos. Although no conclusive evidence links FRBs to wormhole stars, ongoing observations continue to explore this intriguing possibility. Another avenue involves studying gravitational waves, ripples in spacetime caused by violent astrophysical events. The mergers of black holes and neutron stars have already been detected through gravitational wave observatories like LIGO and Virgo. If wormhole core stars exist and interact, perhaps merging or undergoing catastrophic changes, they could produce gravitational wave signatures that differ subtly from those of black holes or neutron stars. Researchers analyze these waveforms to identify potential deviations that could hint at exotic compact objects. Additionally, some scientists examine the motion of stars and gas clouds near the centers of galaxies or in dense stellar clusters, where gravitational effects are extreme. Unexplained perturbations or unusual orbital dynamics might suggest the presence of wormhole core stars, especially if their gravitational influence cannot be attributed to black holes or known compact objects. The search for wormhole core stars also benefits from advancements in computational astrophysics. Researchers create detailed simulations of how such stars would form, evolve, and interact with their environment, predicting observable signatures that astronomers can test. These models help to refine observational strategies and interpret puzzling data. Despite these efforts, no definitive, direct evidence of wormhole core stars has been found so far. The extreme rarity and unusual nature of these objects mean they could be hiding among countless other cosmic phenomena, their signals subtle and easy to misinterpret. Moreover, many exotic effects attributed to wormhole stars could also be explained by more conventional astrophysical processes. Nevertheless, the possibility of discovering wormhole core stars remains a powerful motivation for ongoing research. Future telescopes with higher sensitivity and resolution, like the James Webb Space Telescope's successors or next-generation gravitational wave detectors, could provide the detailed data needed to detect the unique fingerprints of wormhole stars. In the meantime, the quest for indirect evidence continues, pushing the boundaries of both observational technology and theoretical understanding. Confirming the existence of wormhole core stars would revolutionize our grasp of the cosmos, providing concrete proof that space-time tunnels not only exist but are naturally formed and stable within the universe. A wormhole core star, with its exotic internal structure and a stable wormhole embedded at its center, would likely present observational features quite unlike those of conventional stars. While the core wormhole itself remains invisible to direct observation, its profound influence on the star's properties could manifest through unique and unusual signatures detectable with the right instruments. Understanding these potential clues is key for astronomers hoping to identify such extraordinary objects amidst the vastness of space. One of the primary ways a wormhole core star might reveal itself is through its light spectrum, the specific pattern of electromagnetic radiation it emits across different wavelengths. Ordinary stars have well understood spectra shaped by their surface temperature, chemical composition, and atmospheric processes. These spectra often contain characteristic absorption or emission lines corresponding to elements like hydrogen, helium, and metals. In contrast, a wormhole core star's spectrum could deviate markedly from this norm. The intense gravitational and quantum effects near the wormhole throat could alter how energy is emitted or absorbed. For example, matter spiraling toward the wormhole might accelerate to near-light speeds, emitting high-energy radiation such as X-rays or gamma rays. The interaction between normal matter and exotic matter in the star's core could produce spectral lines that do not correspond to any known elements or particles, presenting astronomers with unfamiliar and puzzling signatures. Additionally, the star's gravitational field, intensified and warped by the wormhole, could cause unusual gravitational redshifts. Normally, photons climbing out of a star's gravitational well lose energy, shifting toward longer wavelengths. For a wormhole core star, the redshift patterns might be irregular or stronger than expected for its size and mass, betraying the presence of extreme spacetime curvature. Beyond spectra, gravitational effects offer another window into the nature of wormhole core stars. These stars could produce gravitational lensing effects different from those caused by black holes or neutron stars. Light from background stars or galaxies passing near a wormhole core star might be bent into strange patterns, multiple images, unusual magnification, or brightness fluctuations inconsistent with known models. Detecting such anomalies requires high-resolution observations and careful analysis, but could serve as a smoking gun for wormhole presence. Moreover, the star's gravity might influence nearby objects in unexpected ways. For example, planets or stellar companions orbiting a wormhole core star might experience irregular orbital motions due to the complex gravitational landscape shaped by the wormhole's throat. Precise measurements of such orbital anomalies could hint at the star's exotic interior. Another intriguing possibility is that wormhole core stars might emit strange or transient radiation bursts. Matter interacting with the wormhole could generate sudden flares of energy, potentially explaining some mysterious cosmic phenomena such as fast radio bursts, FRBs, or unexplained gamma-ray flashes. These bursts could arise from matter briefly trapped in the wormhole's throat or accelerated to relativistic speeds before being expelled. Magnetic fields in wormhole core stars might also be atypical. While many stars have magnetic fields generated by plasma flows within, the presence of exotic matter and the wormhole structure could amplify or distort these fields, leading to unusual magnetic phenomena detectable via polarized light or radio emissions. From an observational standpoint, identifying wormhole core stars would likely require combining data across multiple wavelengths: optical, ultraviolet, X-ray, gamma-ray, and radio, to capture the full complexity of their emissions. Additionally, gravitational wave detectors might pick up subtle signals from these stars if they merge or interact dynamically. In essence, a wormhole core star would stand out as an astrophysical enigma, shining with a strange spectral fingerprint, bending light in curious ways, and possibly bursting with unpredictable energy emissions. Detecting and deciphering these signatures would not only confirm the existence of such exotic stars but also open a new window into the fundamental nature of spacetime. Wormhole core stars, by virtue of harboring a stable wormhole at their center, present one of the most extreme examples of spacetime warping imaginable outside of black holes and the immediate vicinity of singularities. Their gravitational fields don't simply follow the predictable patterns established by ordinary stars. Instead, they create profound anomalies in space-time curvature that could fundamentally alter the environment around them. Understanding these gravitational anomalies requires us to delve into how mass energy shapes space-time and how wormholes introduce exotic deviations from conventional gravitational behavior. To begin, it's crucial to recall that gravity, as described by Einstein's general relativity, is not a force acting at a distance but the manifestation of curved space-time. Massive objects like stars and planets create dents, or wells, in the four-dimensional fabric of spacetime, influencing the motion of other bodies and light itself. The degree and nature of this curvature depend on the object's mass, density, and internal structure. In a typical star, spacetime is curved smoothly and symmetrically around its mass. The gravitational potential decreases with distance in a way well characterized by Newtonian gravity for many purposes, though general relativity provides corrections near extremely massive and dense objects. The bending of light around a star, gravitational lensing, is predictable and has been observed extensively. Wormhole core stars, however, disrupt this neat picture profoundly. The presence of a wormhole introduces a non-trivial topology into spacetime, a tunnel that connects two distant regions or even different universes. This means spacetime is not simply curved but also connected, in an exotic way, creating shortcuts that defy conventional geometry. The throat of the wormhole inside the star acts as a conduit where spacetime is severely curved, and the metric, the mathematical description of distances and times, is radically different from that around normal stars. This localized, intense curvature can produce gravitational fields far stronger and more complex than those generated by equivalent masses without wormholes. One immediate consequence is that objects and light rays near a wormhole core star might follow unexpected paths. Instead of smoothly orbiting the star or moving in hyperbolic trajectories past it, their geodesics, paths of least action in curved spacetime, could bend sharply, loop, or even enter the wormhole throat itself. This leads to possible gravitational lensing anomalies, such as multiple images appearing in unusual configurations or brightness fluctuations caused by the dynamic spacetime geometry. Moreover, the gravitational potential near the wormhole throat might exhibit sharp gradients and regions of effective, repulsive gravity, due to the exotic matter stabilizing the wormhole. Unlike normal matter that attracts, exotic matter with negative energy density can generate regions where gravity effectively pushes outward. This could create zones around the star where gravitational attraction weakens or reverses, influencing the orbits of nearby particles and photons. The dynamical behavior of space-time curvature in the vicinity of a wormhole core star might also lead to gravitational waves with unique signatures. Any perturbations, such as matter accreting onto the star or oscillations within the wormhole throat, would ripple through space-time in patterns distinguishable from those produced by black holes or neutron stars. These gravitational waveforms, if detected by sensitive observatories like LIGO, Virgo, or future instruments, could provide indirect evidence of wormhole structures. Furthermore, the gravitational time dilation near a wormhole core star would be extreme and potentially asymmetric. Time dilation occurs when gravity slows the passage of time relative to a distant observer. Near a wormhole throat, the intensity and direction of this dilation might vary in ways unusual for typical stellar objects, possibly allowing clocks near one mouth of the wormhole to tick at vastly different rates than those at the other mouth, or compared to observers far away. These space-time warping effects might also influence the star's own evolution and stability. The distribution of pressure, density, and temperature inside a wormhole core star could be affected by the gravitational anomalies, potentially leading to exotic stellar dynamics unseen in ordinary stars. For instance, matter falling into the wormhole might be channeled away or redistributed, influencing the star's luminosity, magnetic fields, and lifespan. On larger scales, wormhole core stars could distort the surrounding interstellar medium. Gas clouds, cosmic dust, and magnetic fields near such a star would experience unusual gravitational forces, possibly triggering unique emission phenomena or creating regions of anomalous motion detectable with telescopes. Additionally, if the wormhole connects to a distant part of the universe or another universe entirely, the gravitational influence of the star could extend along the tunnel. This could, in theory, allow gravitational interactions or information transfer over vast distances instantaneously, profoundly affecting our understanding of causality and cosmic connectivity. From an observational standpoint, these gravitational anomalies offer potential means to identify wormhole core stars. Precise measurements of stellar orbits, gravitational lensing patterns, time delays in light signals, and gravitational wave signatures could all point toward the presence of such exotic objects. However, detecting and interpreting these anomalies poses significant challenges. Many of the predicted effects could be subtle or confounded by other astrophysical phenomena such as black holes, neutron stars, or dark matter concentrations. Disentangling the unique fingerprints of a wormhole core star requires a combination of multi-wavelength observations, gravitational wave data, and advanced modeling. In summary, wormhole core stars warp spacetime more dramatically than normal stars due to the extreme curvature introduced by their stable wormhole throats. This results in unusual gravitational fields that alter the motion of matter and light, produce distinctive gravitational lensing effects, generate unique gravitational wave signatures, and influence stellar dynamics and evolution. These gravitational anomalies not only challenge our understanding of stellar physics but also offer exciting avenues for detecting and studying these cosmic gateways. Wormhole core stars and black holes are both extraordinary cosmic objects that challenge our understanding of gravity, space-time, and the life cycles of stars. Yet, despite sharing some surface similarities, extreme densities, intense gravitational fields, they are fundamentally different in structure, behavior, and implications for the universe. Understanding these differences illuminates why wormhole core stars are not just exotic curiosities but could represent a whole new class of astrophysical phenomena, distinct from black holes. To begin, black holes form when massive stars exhaust their nuclear fuel and undergo gravitational collapse, compressing their cores to a point where spacetime curvature becomes so intense that an event horizon forms. This horizon is a boundary beyond which nothing, not even light, can escape. Inside this boundary lies a singularity, a point of infinite density where known physics breaks down. Black holes are defined by this event horizon and the singularity hidden within. In contrast, a wormhole core star contains a stable wormhole at its center, a tunnel through spacetime, rather than a singularity surrounded by an event horizon. This distinction is profound. The wormhole throat connects two distant points in spacetime, or potentially different universes, acting as a bridge rather than a dead end. Importantly, wormhole core stars do not trap all matter and radiation irreversibly. Instead, matter might pass through the wormhole throat, potentially emerging elsewhere, making the star a cosmic gateway rather than a cosmic prison. While black holes are characterized by their event horizons, wormhole core stars lack such horizons. This means that, theoretically, information and matter are not lost but can traverse through the wormhole, preserving causality and avoiding the information paradox that plagues black hole physics. The absence of an event horizon implies that wormhole core stars might be observable in ways black holes cannot, as radiation and matter are not irrevocably swallowed but could interact with the outside universe differently. Another key difference lies in their gravitational fields. Black holes have extremely strong and well-understood gravitational fields that curve spacetime to the extreme, with singularities where classical physics fails. Wormhole core stars, while also intensely gravitational, involve exotic matter in their cores with negative energy density. This exotic matter stabilizes the wormhole throat and produces gravitational effects that can include repulsive components, creating regions where gravity pushes outward. Black holes do not have such exotic matter, and their gravity is purely attractive. The internal structure of these objects also diverges. Black holes are often modeled as vacuum solutions to Einstein's equations, surrounded by accretion disks of infalling matter that emit X-rays and other radiation. Wormhole core stars, however, are stellar objects with complex internal dynamics involving exotic matter, quantum effects, and stable wormholes. Their energy production and matter distribution differ fundamentally from the standard black hole accretion scenario. In terms of observational signatures, black holes reveal themselves primarily through their effects on nearby matter, accretion disks emitting X-rays, relativistic jets, gravitational lensing, and now gravitational waves from mergers. Wormhole core stars, with their unique space-time geometries, might exhibit different lensing patterns, unusual spectral lines, or transient radiation bursts tied to matter interacting with the wormhole. Detecting these differences could help astronomers distinguish between the two. Furthermore, wormhole core stars might allow travel or communication through the wormhole throat, at least in theory. Black holes, by contrast, are one-way endpoints where escape is impossible once past the event horizon. This difference opens profound possibilities for wormhole stars as cosmic portals, while black holes remain ultimate gravitational sinks. The evolutionary pathways of these objects also contrast. Black holes result from the death of massive stars or from mergers and accretion in dense environments. Wormhole core stars, if they exist, may form under more exotic conditions involving the presence of exotic matter or quantum gravitational effects during stellar collapse or in primordial environments. Their lifespans, energy output, and interactions with their surroundings might therefore differ substantially from black holes. Lastly, the theoretical challenges they pose differ. Black holes have been studied extensively, with strong supporting observational evidence and well-developed mathematical frameworks, though questions remain about their quantum behavior. Wormhole core stars remain largely speculative, hinging on exotic matter and quantum effects not yet observed directly. Confirming their existence would demand new physics and could revolutionize our understanding of spacetime. In summary, while both black holes and wormhole core stars represent extremes of gravity and stellar evolution, they differ fundamentally. Black holes are defined by event horizons and singularities that trap matter and information irretrievably. Wormhole core stars harbor stable tunnels through spacetime supported by exotic matter, lacking event horizons and potentially connecting distant regions of the universe. These differences in structure, gravitational behavior, observational signatures, and theoretical implications position wormhole core stars as fascinating, distinct cosmic phenomena, possibly bridging the gap between astrophysics and quantum gravity. Throughout the vast expanse of the cosmos, astronomers have observed numerous enigmatic phenomena, mysterious signals, unexplained bursts of energy, and cosmic behaviors that defy conventional astrophysical explanations. From fast radio bursts, FRBs, to unexpected gravitational waves, these mysteries invite speculation about exotic astrophysical objects that might be responsible. Wormhole core stars, with their unique structure and extraordinary properties, offer a tantalizing candidate to potentially explain some of these cosmic puzzles. One of the most perplexing mysteries in contemporary astronomy is the origin of fast radio bursts, intense, millisecond-long pulses of radio waves originating from distant galaxies. Despite numerous detections since their discovery in 2007, the precise mechanisms generating FRBs remain uncertain. Some theories propose exotic neutron stars or magnetars, while others suggest phenomena involving black holes or even extraterrestrial technology. Wormhole core stars provide an intriguing alternative explanation. The stable wormhole at the core of such a star could act as a cosmic accelerator, channeling matter and energy through the tunnel and producing sudden, intense emissions of radiation. Matter spiraling into the wormhole throat might be accelerated to relativistic speeds, releasing bursts of electromagnetic energy detectable as FRBs. The exotic matter stabilizing the wormhole could also facilitate unique quantum interactions, giving rise to transient energy bursts not observed in ordinary astrophysical processes. This could explain the seemingly random, short duration, and highly energetic nature of FRBs. Beyond FRBs, wormhole core stars might also account for some unusual gravitational wave signals detected by observatories like LIGO and Virgo. Certain gravitational wave events have shown patterns that do not neatly fit the expected signatures from black hole or neutron star mergers. If wormhole core stars exist and occasionally merge or experience structural instabilities, the gravitational waves they emit might carry distinctive fingerprints, such as echoes or frequency shifts, that reveal their exotic internal makeup. Moreover, the puzzling phenomenon of ultra-high-energy cosmic rays, particles traveling near the speed of light with energies exceeding those producible by known astrophysical accelerators, could potentially be linked to wormhole core stars. The wormhole tunnel might serve as a natural accelerator, propelling particles through intense gravitational and electromagnetic fields, imparting energies unattainable elsewhere. Wormhole core stars could also shed light on enigmatic gamma-ray bursts, GRBs, the universe's most energetic explosions. While most GRBs are associated with massive stellar collapses or neutron star mergers, some bursts exhibit atypical properties. The dynamic processes occurring near a wormhole throat, matter inflows, exotic particle interactions, and energy released through the tunnel, might generate unique GRB-like signals with signatures different from conventional sources. In addition, wormhole core stars might influence the behavior of dark matter or dark energy, two of the universe's greatest mysteries. Their exotic cores could interact with or trap dark matter particles, affecting the local distribution of this invisible mass and potentially altering galaxy formation or cosmic evolution. If wormholes connect to other regions of the universe or alternate dimensions, they might also provide pathways for energy or information exchange beyond our observable cosmos, contributing to phenomena we currently perceive as unexplained anomalies. Another cosmic mystery potentially illuminated by wormhole core stars is the observation of certain quasars and active galactic nuclei that display rapid variability or emissions inconsistent with known physical models. The presence of a wormhole star near or within these systems could alter gravitational and electromagnetic environments, causing unusual flares or changes in brightness that challenge standard explanations. Furthermore, the concept of wormhole core stars touches upon the possibility of time anomalies observed in astrophysical data. The extreme space-time curvature near wormhole throats might lead to time dilation effects or causality violations that manifest as signals appearing to originate before their cause or exhibiting unexpected temporal behavior. Such phenomena have been hinted at in some astrophysical observations but remain poorly understood. While these speculations remain on the frontier of theoretical astrophysics, the possibility that wormhole core stars could explain some of the cosmos's strangest and most persistent mysteries offers a compelling motivation for further study. Detecting these stars or their effects would not only solve specific puzzles but fundamentally alter our understanding of the universe's structure and the nature of spacetime itself. In this light, wormhole core stars represent more than theoretical curiosities. They may be the keys to unlocking profound cosmic secrets, bridging gaps between observation and theory, and expanding the horizons of human knowledge. The hypothetical size and lifespan of wormhole core stars are topics of immense complexity and intrigue, merging astrophysical principles with speculative physics to imagine objects unlike any known stellar body. Unlike conventional stars, whose sizes and lifespans are relatively well understood thanks to decades of observation and theoretical modeling, wormhole core stars introduce exotic factors, such as the presence of a stable wormhole and exotic matter, that complicate these fundamental characteristics. Exploring how these elements might influence the star's dimensions and longevity opens new horizons in our understanding of stellar evolution and the dynamics of spacetime. In considering the size of wormhole core stars, it is important to recognize that the wormhole at the star's center fundamentally alters its internal structure. Normal stars are held in hydrostatic equilibrium, balancing the outward pressure from nuclear fusion against the inward pull of gravity. This equilibrium dictates their radius, mass, and density profiles. For wormhole core stars, the presence of a stable wormhole throat supported by exotic matter adds a novel internal component that can influence this balance. Theoretically, wormhole core stars could vary widely in size. Some models suggest that these stars might be similar in mass and radius to neutron stars, extremely dense remnants of massive stars, typically around 1.4 times the mass of our Sun but only about 20 kilometers in diameter. In such cases, the wormhole core would be a compact, highly curved region at the center, stabilized by exotic matter that prevents collapse into a black hole. The size of the wormhole throat itself might be microscopic or macroscopic, ranging from subatomic scales to several kilometers across, depending on the exotic matter properties and quantum effects involved. Alternatively, wormhole core stars could be substantially larger, perhaps comparable to or exceeding typical stellar radii. If the exotic matter distribution extends beyond the core and modifies the star's internal pressure gradients, the star's radius could be inflated or distorted relative to normal stars of similar mass. This might result in stars with unusual density profiles, dense cores harboring the wormhole, surrounded by extended envelopes of plasma or exotic matter. Such stars might resemble supergiants in size but differ drastically in internal composition and behavior. The exact size range remains uncertain due to the theoretical nature of these objects and the lack of observational constraints. However, it is plausible that wormhole core stars span a continuum from compact, neutron star-like bodies to larger, more diffuse objects, contingent on formation mechanisms and environmental factors. Turning to the lifespan of wormhole core stars, we encounter another layer of complexity. A star's lifespan traditionally depends on its mass and fuel consumption rate. Massive stars burn fuel quickly and live short lives, while smaller stars sustain fusion longer. Wormhole core stars challenge this framework by introducing the possibility that energy dynamics within the star are altered by the wormhole's presence. The wormhole throat, stabilized by exotic matter, might serve as a channel for matter and energy to flow into or out of the star, potentially changing how fuel is supplied, consumed, or redistributed. For instance, matter could be funneled through the wormhole, effectively feeding or depleting the star's nuclear fuel reserves in unconventional ways. This could either extend or shorten the star's lifespan depending on the direction and rate of matter transfer. Exotic matter itself might contribute to energy generation or pressure support within the star, supplementing or replacing conventional nuclear fusion in maintaining equilibrium. If the exotic matter exhibits negative energy density or repulsive gravitational effects, it could reduce the star's core pressure requirements, potentially slowing fusion rates and prolonging the star's active phase. Quantum effects near the wormhole throat might also influence decay rates of particles or alter nuclear reaction pathways, further modifying the star's lifespan. Such effects remain highly speculative but highlight the intricate interplay between quantum mechanics and astrophysics in these exotic objects. Moreover, the stability of the wormhole is crucial to the star's longevity. If the exotic matter distribution fluctuates or diminishes, the wormhole might begin to collapse, triggering catastrophic changes in the star's structure. Such an event could lead to rapid collapse into a black hole or an explosive dispersal of stellar material, drastically shortening the star's life. On the other hand, A stable wormhole maintained over cosmological timescales could enable a wormhole core star to persist far longer than comparable conventional stars. The wormhole might act as a pressure valve or energy conduit, preventing typical end-of-life collapse scenarios and allowing the star to endure as a unique astrophysical entity. Environmental factors, such as interactions with nearby stars, accretion of matter, or exposure to cosmic radiation, would also influence the star's lifespan. The exotic gravitational field and space-time curvature might shield or expose the star differently compared to normal stars, impacting its evolution. In summary, the hypothetical size of wormhole core stars ranges from compact, neutron star-like scales to potentially much larger, more diffuse structures shaped by exotic matter and space-time geometry. Their lifespans are similarly variable and influenced by novel energy dynamics introduced by the wormhole throat, the behavior of exotic matter, and quantum effects. These stars could live shorter or longer lives than ordinary stars of similar mass, depending on the delicate balance of matter and energy flows through the wormhole. Understanding these aspects requires advances in theoretical modeling, quantum gravity, and astrophysical observation, as wormhole core stars challenge many assumptions of stellar physics. If discovered, they would compel us to rethink the life cycles of stars and the fundamental connections between gravity, quantum mechanics, and cosmology. Exotic matter is at the heart of the mystery surrounding wormhole core stars, serving as the critical ingredient that could allow such stars to harbor stable, traversable wormholes. Unlike ordinary matter, the protons, neutrons, electrons, and photons that compose everything we see around us, exotic matter possesses theoretical properties that defy everyday intuition and the conventional laws of physics as we understand them. Understanding the nature of exotic matter and its role in stabilizing wormholes is key to grasping how wormhole core stars might exist in reality, and why they would differ fundamentally from ordinary stars. In classical physics and general relativity, matter and energy are always expected to have positive energy density. That is, energy is always positive, and gravity is always attractive. Exotic matter, however, is hypothesized to violate these energy conditions, exhibiting negative energy density or negative mass effects. This means that in certain configurations, exotic matter would produce repulsive gravity, pushing outward against the usual inward pull of gravity generated by normal matter. The theoretical requirement for exotic matter arises directly from the mathematics of traversable wormholes. When Einstein's field equations are solved for a spacetime containing a wormhole, the solutions typically demand that the wormhole's throat is held open against gravitational collapse by a source of negative energy density. Without this, the throat would pinch off almost instantaneously, making the wormhole non-traversable. But what exactly could this exotic matter be? While no known particles or materials in everyday physics qualify, quantum field theory provides some hints. Quantum phenomena such as the Casimir effect demonstrate that vacuum fluctuations in the quantum fields can produce regions of negative energy density under specific, highly controlled conditions. Between two very close conducting plates, the energy density can be lower than the surrounding vacuum, effectively generating a pocket of negative energy. Although this effect is tiny and occurs on microscopic scales, it proves that exotic energy conditions can exist, at least in principle. In the extreme environment inside a wormhole core star, it is speculated that such quantum effects might be amplified or stabilized by the star's intense gravitational and electromagnetic fields. The star's core could maintain a persistent distribution of exotic matter, possibly a new form of quantum field or particle not yet detected, that generates the necessary negative energy density to prevent the wormhole from collapsing. Another candidate for exotic matter comes from hypothetical fields such as phantom energy, or scalar fields with unusual properties. Phantom energy, a proposed form of dark energy with a strongly negative pressure exceeding that of the cosmological constant, could provide the repulsive gravitational force needed. Scalar fields, which assign a single value to every point in space and time, might under certain conditions exhibit negative energy densities, particularly in highly curved spacetime regions near the wormhole throat. The exotic matter inside the wormhole core star would not only provide the outward pressure to counteract gravity, but also modify the star's internal dynamics. Because exotic matter violates normal energy conditions, it might allow for unusual configurations of matter and energy, enabling the star to remain stable despite the presence of intense gravitational fields and quantum effects. Importantly, the exotic matter must be distributed precisely in and around the wormhole throat to maintain stability. Too little exotic matter, and the wormhole collapses. Too much or unevenly distributed exotic matter, and the star's structure could become unstable or lead to singularities. Theoretical models often consider thin shell distributions, where exotic matter is concentrated in a narrow region surrounding the wormhole throat, minimizing the total exotic matter required while maximizing stability. This delicate balance is challenging because exotic matter is not only hypothetical but also tends to raise paradoxes and complications in theoretical physics, such as violations of causality or energy conservation. Nonetheless, if a star's core can sustain a stable pocket of exotic matter, it would create the perfect environment for a traversable wormhole, effectively turning the star into a cosmic gateway. From an astrophysical perspective, the presence of exotic matter inside the star could produce observable effects. For instance, the exotic matter's repulsive gravity might alter the star's gravitational field, producing anomalies detectable via gravitational lensing or orbital dynamics of nearby objects. Additionally, interactions between exotic matter and normal matter might generate unusual radiation signatures or influence the star's magnetic field configuration. Furthermore, exotic matter could affect the star's lifespan and evolution. By providing an additional pressure component, it might prevent gravitational collapse or delay it significantly, allowing the Wormhole Core Star to persist far longer than conventional stars of similar mass. In conclusion, exotic matter is the cornerstone of the Wormhole Core Star hypothesis. Its unique theoretical properties, negative energy density and repulsive gravity, are essential for stabilizing the wormhole throat against collapse. While exotic matter remains elusive and speculative, its role in wormhole physics opens the possibility that wormhole core stars could exist as stable, observable objects in our universe, bridging the gap between the realms of astrophysics and quantum gravity. Theoretical models and simulations aiming to recreate wormhole core stars are at the cutting edge of astrophysics, quantum gravity, and computational physics. While direct observation of such stars remains elusive, scientists use advanced mathematical frameworks and computer simulations to explore the physical plausibility, stability, and potential observational signatures of these exotic objects. These models blend Einstein's general relativity with quantum field theory and often rely on numerical relativity techniques to solve the complex equations governing wormholes embedded within stellar matter. One of the earliest and most influential approaches to modeling wormholes inside stars involves solving the Einstein field equations with exotic matter distributions designed to sustain a stable wormhole throat. Researchers begin with idealized, metric functions that describe spacetime geometry incorporating a wormhole structure. By imposing conditions such as traversability, no event horizon, stability, no immediate collapse, and smooth matching between wormhole interiors and stellar exteriors, these models create theoretical blueprints of wormhole core stars. Simulations often explore how exotic matter can be arranged inside a star to prevent wormhole collapse. For example, the so-called thin shell wormhole model treats the wormhole throat as a thin layer of exotic matter, sandwiched between normal stellar matter layers. Computational studies solve the coupled differential equations describing pressure, density, and space-time curvature in these regions, examining parameter ranges where equilibrium is achieved. These simulations show that under certain exotic matter equations of state, stable configurations can exist that mimic the internal structure of wormhole core stars. More recent numerical relativity simulations utilize supercomputers to evolve wormhole space-time metrics dynamically, studying how such stars form, evolve, and respond to perturbations. These time-dependent simulations test the stability of wormhole cores when subjected to realistic astrophysical processes such as matter accretion, stellar oscillations, or gravitational wave emission. By varying the properties of exotic matter and initial conditions, these models map the parameter space in which wormhole core stars could realistically persist. Another line of research incorporates quantum effects through semi-classical gravity. Here, the backreaction of quantum fields on space-time geometry is included to assess whether quantum fluctuations can stabilize or destabilize wormholes inside stars. Such models often use the framework of the Casimir effect or vacuum polarization to simulate the exotic negative energy densities needed. While computationally intensive, these simulations suggest scenarios where quantum effects significantly enhance wormhole stability, potentially extending the lifetime of wormhole core stars. Additionally, some theoretical studies explore the role of modified gravity theories, extensions or alternatives to general relativity that naturally allow for exotic matter effects or violations of classical energy conditions. Within these frameworks, wormhole solutions are more readily obtained, and simulations investigate how such wormholes could exist inside stars without requiring unrealistically exotic matter. These alternative gravity models provide fertile ground for simulating wormhole core stars with fewer theoretical constraints. Simulation results also predict possible observational features, helping astronomers design searches for wormhole core stars. For example, models show how gravitational lensing patterns and radiation emissions differ from those of conventional stars, offering testable signatures. Some simulations indicate that wormhole core stars might emit characteristic gravitational wave echoes, following perturbations, a novel signal that upcoming detectors might detect. While no fully realistic, observationally confirmed simulation of a wormhole core star exists yet, ongoing progress in computational astrophysics and quantum gravity is rapidly advancing the field. Researchers continue to refine models, incorporate more physics, and push simulations toward realistic astrophysical scenarios, including star formation, evolution, and interaction with their environments. In summary, theoretical models and scientific simulations of wormhole core stars combine general relativity, exotic matter physics, quantum effects, and advanced computational techniques to explore these extraordinary objects' plausibility and characteristics. Although still speculative, these efforts are essential for guiding observational searches and deepening our understanding of the fundamental structure of spacetime. Speculating on the possible destinations through a wormhole core star's stable wormhole throat invites us into one of the most fascinating realms of theoretical physics and cosmology, a realm where the boundaries of space, time, and even reality itself may be bridged or transcended. The question of where such a wormhole might lead is deeply tied to the nature of spacetime, the multiverse hypothesis, and the structure of the cosmos at its most fundamental level. Although the specifics remain speculative, the possibilities offer a thrilling window into cosmic wonder and the unknown. The simplest and most conservative possibility is that the wormhole core star's tunnel connects two distant regions within our own universe. In this scenario, the wormhole acts as a cosmic shortcut, linking locations that would otherwise be separated by immense stretches of space, millions or billions of light-years apart. Instead of traveling through the intervening space, matter and information passing through the wormhole could emerge instantaneously or with drastically reduced travel time on the other side. Such a shortcut would revolutionize our understanding of cosmic distances and communication, potentially enabling rapid interstellar or even intergalactic travel. The implications for astrophysics and future space exploration are profound. Civilizations could traverse vast cosmic distances in ways currently deemed impossible. However, this scenario also poses profound questions about causality and the nature of space. Would such shortcuts create paradoxes or closed time-like curves allowing travel backward in time? Expanding beyond our universe, wormhole core stars could connect to parallel universes or alternate realities as envisioned in various multiverse theories. The multiverse concept arises from different lines of theoretical physics, including inflationary cosmology, string theory landscapes, and quantum mechanics interpretations. These theories suggest that our universe might be one of countless others, each with different physical laws, constants, or histories. If a wormhole core star's throat opens into a parallel universe, the gateway might link vastly different physical realms. The destination could be a universe with altered fundamental constants, where the strength of gravity, the speed of light, or particle masses differ, yielding exotic physics and potentially unfamiliar forms of matter and energy. Traveling through such a wormhole would be an unprecedented journey into the unknown, with unknown hazards and possibilities. In some models, parallel universes exist in higher dimensional spaces beyond our familiar three spatial dimensions and time. Wormholes might provide access to these extra dimensions, bridging not only distant locations but also distinct dimensional realms. These higher dimensional pathways could circumvent the limits imposed by our four-dimensional spacetime, allowing shortcuts or even transitions into different physical laws or modes of existence. Beyond spatial or dimensional displacement, wormhole core stars might facilitate travel through time itself. In certain solutions to Einstein's equations involving wormholes, the tunnel's mouths can be separated temporally as well as spatially. This raises the theoretical possibility of using a wormhole as a time machine, traveling to the past or future relative to an external observer. However, such time travel scenarios encounter paradoxes and theoretical challenges, including the so-called grandfather paradox, and potential violations of causality. The wormhole's internal geometry might also be dynamic or evolving. It could connect not to a fixed destination but to a region of spacetime that changes over time. Perhaps a young universe in its early expansion, a collapsing universe approaching a big crunch, or even a singularity beyond a black hole's event horizon in another cosmos. This dynamic connectivity could link wormhole core stars to some of the most extreme environments in theoretical cosmology. Another speculative destination involves the quantum foam, the hypothesized turbulent, frothy structure of spacetime at the Planck scale, 10⁻⁵35 meters. Wormholes might emerge as transient features within this quantum foam, and stable wormholes embedded in stars could act as portals into this microscopic domain. This could provide a gateway to a realm governed by quantum gravity, where classical notions of space and time break down, and novel physical laws operate. In all these possibilities, the destination depends critically on the wormhole's global topology and boundary conditions, which remain highly uncertain in current physics. Whether a wormhole connects to a remote star system in our galaxy, an alternate universe with strange physics, or a higher dimensional realm beyond our senses depends on the underlying theory of quantum gravity and the initial conditions of the wormhole's formation. From a practical standpoint, any journey through such a wormhole would face enormous challenges. Traversing a wormhole might expose travelers to intense tidal forces, exotic radiation, or instabilities. The nature of the exotic matter stabilizing the wormhole could impose limits on passage, such as size constraints, or the necessity of specific energy inputs to keep the tunnel open. Nevertheless, the concept of wormhole core stars as cosmic gateways to other parts of our universe, parallel universes, extra dimensions, or even different times remains one of the most captivating ideas in modern astrophysics. It challenges our deepest assumptions about the universe's structure and invites us to imagine a cosmos interconnected in ways previously confined to science fiction. The realization of such connections would revolutionize physics, cosmology, and potentially the future of exploration. It would transform our understanding of space and time from static arenas to dynamic, interwoven fabrics with portals bridging vast cosmic distances and realities. The idea that wormhole core stars could enable time travel or provide shortcuts through time is one of the most intriguing and mind-bending possibilities arising from the theoretical physics of wormholes. While the concept of time travel has long captured human imagination, from science fiction tales to philosophical debates, modern physics provides frameworks where such phenomena might be mathematically conceivable, particularly through the lens of wormhole spacetimes. Wormhole core stars, with their stable, naturally occurring wormholes at their centers, could be cosmic entities where these exotic effects manifest. Exploring how and whether they might facilitate time travel reveals a fascinating intersection of relativity, quantum theory, and causality. In Einstein's general relativity, spacetime is a four-dimensional fabric that can be curved, twisted, or connected in complex ways. Wormholes are hypothetical, shortcuts, or tunnels through this fabric, connecting two distinct points in spacetime. Unlike a simple spatial shortcut, these points may differ not only in their spatial coordinates, but also in their temporal coordinates, meaning the two wormhole mouths could exist at different times as well as different places. This temporal aspect arises from relativistic effects related to time dilation. Imagine one mouth of a wormhole is accelerated at speeds close to light or placed in a strong gravitational field, causing time to pass differently relative to the other mouth. After the acceleration ends, an observer could find that time at one mouth has passed more slowly or quickly than at the other. This desynchronization means that entering one mouth could lead to emerging at the other mouth at a different time, potentially traveling into the past or future relative to an external observer. If wormhole core stars harbor such stable wormholes, their unique environments might naturally create or maintain these temporal differences. For instance, intense gravitational fields, quantum effects, or stellar motion could cause the mouths of the wormhole to experience differing rates of time passage, effectively turning the wormhole into a time machine. However, the possibility of time travel through wormholes is fraught with theoretical challenges and paradoxes. One of the most famous paradoxes is the grandfather paradox, where a time traveler might prevent their own existence by altering past events. Resolving these paradoxes requires new physics or interpretations, such as the many worlds hypothesis, where each action creates a new branch of reality, or the chronology protection conjecture, proposed by Stephen Hawking, which suggests that the laws of physics prevent time travel on macroscopic scales to preserve causality. Another issue is the stability of such time-traveling wormholes. Many theoretical studies indicate that quantum effects or vacuum fluctuations would destabilize a wormhole if used for time travel, causing it to collapse or generate destructive feedback. However, if exotic matter within a wormhole core star can provide continuous negative energy to stabilize the throat, it might prevent such collapse, allowing time travel to be sustained, at least temporarily. The exotic matter's properties could also influence the direction and duration of time travel. For example, certain configurations might only allow travel into the future or limit how far into the past a traveler could go. The interplay between quantum mechanics and general relativity in these stars is critical for understanding these limitations. From a practical perspective, traveling through a wormhole in a wormhole core star to the past or future would entail extraordinary hazards. The traveler would face intense gravitational gradients, tidal forces, exposure to exotic radiation, and potential disruption of spacetime itself. Moreover, it remains unclear if macroscopic objects or information can safely transit without destruction. If time travel is possible through wormhole core stars, it could have profound implications for physics, philosophy, and technology. It might provide a natural laboratory to test fundamental principles, explore the nature of causality, and probe the quantum structure of spacetime. On the speculative front, advanced civilizations might harness such stars to explore their own past or future or communicate across time. However, many physicists caution that time travel may remain a theoretical curiosity. The constraints imposed by quantum gravity, the requirement for exotic matter, and the potential for paradoxes mean that if wormhole-based time travel exists, it may be exceedingly rare or limited in scope. In conclusion, wormhole core stars embody some of the most extraordinary ideas about time, space, and reality. Their stable wormholes could, in theory, create pathways not just across vast cosmic distances but across time itself. Whether these stars truly enable time travel depends on unresolved questions at the frontiers of physics. Questions that ongoing theoretical research and future astronomical observations might one day answer. Traveling through a wormhole core star, or more precisely, attempting to pass through the stable wormhole at its center, represents an endeavor fraught with extreme and potentially insurmountable physical dangers. While wormhole core stars tantalize us with the prospect of cosmic shortcuts or gateways to other universes, the journey through such an object would not be akin to ordinary space travel. Instead, it involves navigating an environment of extreme gravitational forces, exotic matter, intense radiation, and unknown quantum phenomena, any of which could pose fatal hazards to travelers or spacecraft. One of the most immediate and formidable dangers arises from tidal gravitational forces, often referred to as spaghettification, in the context of black holes. These forces occur because gravity's strength varies dramatically over short distances near extremely compact or dense objects. In a wormhole core star, the curvature of spacetime near the wormhole throat is predicted to be extraordinarily intense, potentially even exceeding that near a black hole's event horizon. As an object approaches the wormhole throat, differential gravitational pulls stretch and compress it in different directions. This tidal stress can elongate matter into thin strands and rip it apart at the atomic level. For any living being or spacecraft, surviving such forces would be nearly impossible without technology or protective mechanisms far beyond current human capabilities. Another hazard relates to the exotic matter hypothesized to stabilize the wormhole. While exotic matter itself remains theoretical and poorly understood, its unusual properties, such as negative energy density and repulsive gravity, could have unpredictable interactions with normal matter and radiation. Passing through regions dense with exotic matter might expose travelers to intense, unfamiliar fields that disrupt atomic structures, interfere with electronics, or cause unknown forms of radiation damage. The radiation environment near a wormhole core star is also expected to be extreme. Stars, by their nature, emit vast amounts of electromagnetic radiation across the spectrum, X-rays, gamma rays, and other high-energy photons. The unique spacetime curvature and exotic matter of a wormhole core star might amplify or modify these emissions, producing radiation of unusual intensity or spectral properties. Radiation hazards would pose lethal threats to biological life and fragile instrumentation. Moreover, the dynamic behavior of matter as it approaches and passes through the wormhole throat could create violent plasma jets, shock waves, or bursts of energetic particles. These energetic phenomena might be the result of matter accelerating to relativistic speeds, interacting with intense magnetic fields, or undergoing rapid compression and heating. Such turbulent plasma environments would complicate navigation and survival. From a quantum perspective, the region around a wormhole throat may exhibit quantum instabilities. Vacuum fluctuations, particle-antiparticle pair creation, or other quantum field effects might create unpredictable and hazardous conditions. These effects could generate transient bursts of exotic particles or radiation, interfere with atomic and molecular structures, or produce chaotic space-time fluctuations that make traversal dangerous or impossible. There is also the risk of encountering causal paradoxes or temporal anomalies. If the wormhole allows passage through time as well as space, travelers might experience disorienting or damaging effects from time dilation or closed time-like curves. Such phenomena could induce unknown biological or physical stresses. The structural stability of the wormhole itself presents another danger. While theorized to be stable due to exotic matter, wormholes might be prone to sudden collapse triggered by perturbations such as matter influx, radiation bursts, or gravitational waves. A traveler caught within a collapsing wormhole could be subjected to extreme tidal forces or trapped irreversibly in a singularity or disconnected region of spacetime. Additionally, navigation through a wormhole core star would be extraordinarily challenging. The intense curvature and exotic matter distributions would likely distort conventional spatial references and communications, making guidance systems unreliable. Without precise control, travelers risk becoming lost, trapped, or crushed. Beyond the wormhole throat, the destination environment is itself an unknown hazard. Emergence could occur in regions with drastically different physical laws, intense radiation, or hostile gravitational conditions. Travelers would need to survive not only the journey through the wormhole, but also potentially alien and dangerous cosmic realms. In summary, the dangers of traveling through a wormhole core star include extreme tidal gravitational forces capable of destroying matter at atomic levels, exposure to exotic matter with unpredictable and possibly harmful properties, intense and unusual radiation environments, violent plasma phenomena and energetic particle bursts, quantum instabilities and vacuum fluctuations producing hazardous effects, potential temporal anomalies causing biological and physical stress, risk of wormhole collapse trapping or destroying travelers, navigation difficulties due to distorted spacetime and communications, unknown hazards at the wormhole's exit point, potentially in alien universes or dimensions. These dangers paint a sobering picture. While wormhole core stars may offer extraordinary possibilities for cosmic travel, Any journey through them would require technology and understanding far beyond current human capabilities. Protective shielding, advanced navigation systems, and deep knowledge of exotic physics would be essential. Even then, survival might not be guaranteed. This stark reality places Wormhole Core Stars more in the realm of speculative astrophysics and futuristic exploration than near-term practical travel options. Yet the very possibility of their existence challenges scientists to push the boundaries of physics, to understand extreme environments, and to imagine the ultimate frontiers of cosmic navigation. The prospect of life existing near a wormhole core star presents a captivating yet profoundly complex question, sitting at the intersection of astrophysics, biology, and the unknown frontiers of exotic physics. To contemplate whether planets, or even life itself, could form and persist in the vicinity of such an extraordinary star requires examining numerous factors, from the star's physical environment and radiation output to the gravitational and space-time distortions caused by the stable wormhole at its center. At first glance, the environment around a wormhole core star might appear exceedingly hostile to life. The intense gravitational fields and warped space-time geometry inherent to such a star would create conditions very different from those around typical stars like our Sun. These extreme conditions could disrupt planetary orbits, produce hazardous radiation levels, and generate exotic particle fluxes, all of which could challenge the formation or sustainability of life-supporting planets. Yet, to determine the likelihood of planets orbiting such a star, one must consider the star's size, lifespan, and stability. If a wormhole core star resembles neutron stars or other compact stellar remnants in size but maintains long-term stability due to its wormhole, it might exert strong but steady gravitational influence over a surrounding planetary system. In such a system, planets could potentially exist in stable orbits at distances where tidal forces and radiation levels are moderated enough to allow complex chemistry and, perhaps, life-supporting conditions. The wormhole's presence introduces unique considerations. The gravitational anomalies near the wormhole throat could create localized regions of unusual space-time curvature. These might manifest as gravitational lensing effects or gravitational gradients that could destabilize closed-in planetary orbits or cause orbital precession. However, planets sufficiently far from the core, beyond the immediate influence of the wormhole's intense curvature, might orbit relatively normally. Radiation levels present another major challenge. Wormhole core stars, like many compact stars, might emit high-energy radiation such as X-rays and gamma rays, intensified or modified by the wormhole's exotic physics. This radiation could sterilize planetary surfaces or prevent stable atmospheres from forming. However, planetary magnetic fields, thick atmospheres, or subsurface oceans might provide protective shields, akin to how Earth's magnetic field protects life from solar and cosmic radiation. The exotic matter stabilizing the wormhole could also affect the local environment. While its properties are not well understood, interactions between exotic matter and normal matter or radiation might produce phenomena that complicate planetary habitability. On the other hand, exotic matter's repulsive gravity effects might reduce accretion rates of harmful stellar wind or cosmic rays, potentially creating niches where life could endure. Considering the broader astrophysical context, wormhole core stars could be rare and isolated, limiting opportunities for planetary system formation. Star formation typically occurs in molecular clouds rich in gas and dust. If wormhole core stars are remnants of unusual evolutionary paths or require exotic conditions to form, they might lack typical protoplanetary disks or nearby material to seed planet formation. Nonetheless, if a wormhole core star resides in a dense stellar environment such as a globular cluster or a galactic core, it might capture or retain planets through gravitational interactions or survive in a multi-star system where complex dynamics allow planet retention. Speculating about life near wormhole core stars also invites us to consider life forms adapted to extreme or exotic environments. Life on Earth demonstrates remarkable resilience, thriving near hydrothermal vents, under ice sheets, or in radiation-rich zones. It is conceivable that life in the vicinity of a wormhole core star, if it exists, would be fundamentally different, perhaps based on exotic chemistry or adapted to withstand intense gravitational and radiation stresses. Moreover, the stable wormhole itself might influence the evolution or distribution of life. If the wormhole connects to other regions of space or universes, it could facilitate the transfer of matter, energy, or even biological material across cosmic distances, seeding life or influencing ecosystems in unexpected ways. In summary, while the extreme gravitational fields, radiation, and exotic matter environment near a wormhole core star pose formidable challenges to planetary formation and life, it is not impossible that planets could orbit at safe distances with conditions suitable for life. Theoretical possibilities include stable planetary orbits beyond the wormhole's immediate gravitational influence, protective planetary magnetic fields or atmospheres shielding life from radiation, life forms adapted to extreme conditions or exotic physics, potential exchange of matter or information through the wormhole affecting habitability. The question remains open and tantalizing, inviting further theoretical modeling and observational efforts to identify candidates for such exotic stellar systems. Harnessing wormhole core stars for interstellar or even interuniversal travel is among the most audacious and transformative ideas in theoretical astrophysics and futuristic space exploration. The concept evokes visions of civilizations utilizing natural cosmic gateways to traverse vast distances instantaneously or bridge entire universes, rewriting the rules of travel, communication, and even human destiny. Yet, such ambitions rest on an intricate interplay of physics, engineering, and unknown exotic phenomena that make the practical use of wormhole core stars one of the greatest challenges imaginable. First, consider the unparalleled advantages that harnessing a wormhole core star might offer. Unlike conventional spacecraft limited by fuel, speed, and time, a stable wormhole at the star's core could provide a direct shortcut through space-time, allowing matter, energy, and information to pass instantly or near-instantly between two distant points. This would eliminate the multi-generational voyages and relativistic time dilations associated with near-light speed travel, opening possibilities for rapid exploration and communication across the galaxy, or even between universes if the wormhole connects parallel dimensions. To harness such a star, one would need to identify or create access points to the wormhole's entrance and exit, control the flow of matter through the tunnel, and ensure safe transit conditions. Here, the unique nature of wormhole core stars might assist. The wormhole is embedded naturally within the star's structure, perhaps accessible through the star's surface or magnetosphere, offering a stable portal, unlike artificially created wormholes that might require vast energies to sustain. Engineering challenges abound. First, approaching and entering a wormhole core star demands technology capable of withstanding extreme tidal forces, radiation, and exotic matter environments described earlier. Shielding spacecraft and passengers from these hazards would require advanced materials or fields, potentially involving magnetic or gravitational shielding technologies far beyond current human capabilities. Once inside, precise navigation and control systems must manage the journey through the wormhole, which could involve unpredictable space-time curvature, fluctuating throat sizes, or dynamic gravitational conditions. Real-time monitoring and adaptive control would be essential to prevent damage or loss. Another crucial factor is the wormhole's stability and traversability. Even if the wormhole is naturally stabilized by exotic matter inside the star, the influx of matter and energy from travelers might disturb this delicate balance. Harnessing the wormhole effectively may necessitate methods to regulate the exotic matter distribution or inject negative energy to maintain throat stability, a feat requiring deep understanding and manipulation of quantum gravity phenomena. On a larger scale, controlling wormhole core stars for travel would demand understanding their astrophysical environments. Coordinating travel schedules, predicting wormhole behavior, and securing safe entry points amidst intense stellar radiation and gravitational anomalies require comprehensive astrophysical models and continuous observation. Moreover, the destinations of wormhole core stars may not be predetermined or fixed. If the wormhole leads to other universes or dynamic space-time regions, the exit point might shift or vary with time, complicating navigation and mission planning. Harnessing these stars might involve technology to stabilize or lock wormholes onto desired endpoints, an area still purely theoretical. From an energy perspective, the ability to tap into or harness the wormhole's properties could revolutionize propulsion and energy generation. If matter-energy conversion processes near the wormhole core can be controlled, it might yield new energy sources or propulsion methods based on space-time manipulation rather than conventional fuel. At a civilization scale, harnessing wormhole core stars would profoundly impact exploration, colonization, and communication. Instantaneous travel across vast distances could connect distant star systems, facilitating the spread of life, culture, and knowledge. Interuniversal travel, if possible, could open entirely new realms for discovery and expansion. Philosophically and strategically, civilizations capable of harnessing wormhole core stars would wield extraordinary power and face unique responsibilities. Control over such gateways could confer dominance over galactic or multiversal networks but also risks catastrophic consequences if mishandled, such as wormhole collapse, causality violations, or exposure to unknown exotic phenomena. Current human technology and understanding fall far short of enabling harnessing wormhole core stars. However, research into exotic matter, quantum gravity, high-energy astrophysics, and advanced materials gradually advances the theoretical foundation necessary for future endeavors. Projects exploring gravitational wave astronomy, black hole physics, and high-energy cosmic phenomena indirectly contribute to this knowledge. In summary, while harnessing wormhole core stars for travel remains speculative and technologically distant, the concept embodies a transformative vision for cosmic exploration. It promises instantaneous connection across vast distances or even different universes, redefining the boundaries of space, time, and human possibility. Unlocking this potential would require breakthroughs in physics, engineering, and cosmic understanding unparalleled in history. Detecting wormhole core stars presents one of the most profound challenges in modern astrophysics, largely because these extraordinary objects, if they exist, blend exotic theoretical physics with observational subtlety. Their very nature defies straightforward identification, pushing the limits of current astronomical instrumentation and analysis techniques. To understand why wormhole core stars remain elusive, it's essential to explore the fundamental hurdles posed by their unique physical characteristics, the limitations of existing observational methods, and the subtlety of their expected signatures. First and foremost, wormhole core stars are hypothesized to be extremely rare and possibly isolated objects. Their formation requires conditions far beyond typical stellar evolution, such as the presence of exotic matter, extreme density fluctuations, or quantum effects that are not commonly found in the cosmos. This rarity alone means the odds of identifying such a star within the vastness of the observable universe are low, akin to finding a cosmic needle in an immense haystack. Moreover, wormhole core stars are likely to be compact and highly dense, perhaps similar in scale to neutron stars or black holes. Such objects emit little visible light, often radiating primarily in high-energy bands like X-rays or gamma rays. Their radiation can be faint, transient, or masked by more conventional astrophysical sources. Distinguishing the subtle differences between the emissions of a wormhole core star and those of other compact objects requires highly sensitive instruments and sophisticated data analysis methods, many of which are still in development. Another core challenge lies in the lack of direct observational markers unique to wormhole core stars. Their defining feature, a stable wormhole at the core, is hidden beneath layers of stellar material and exotic matter. Unlike black holes, which can be identified by their event horizons and characteristic accretion disks, wormhole core stars might not produce such overt signals. Instead, they may exhibit subtle anomalies in gravitational lensing, spectral emissions, or gravitational wave patterns, all of which can be mimicked by other astrophysical phenomena. The wormhole's gravitational effects might cause unusual space-time distortions near the star, but detecting these requires extremely precise measurements of light bending, timing of pulsars, or gravitational wave signatures. Current instruments, while powerful, often lack the resolution or sensitivity to isolate these effects conclusively, especially given the noise from cosmic background sources and intervening matter. Additionally, the presence of exotic matter, which theoretically stabilizes the wormhole, complicates detection. Exotic matter does not interact with electromagnetic radiation in standard ways and may not emit light or particles detectable by conventional telescopes. This invisibility means much of the Wormhole Core Star's mass-energy distribution might be hidden from direct observation, requiring indirect inference through gravitational or quantum effects. The dynamic nature of wormhole cores could further obscure detection. If the wormhole's throat fluctuates or oscillates due to internal or external perturbations, its observational signatures might be transient or irregular, complicating efforts to identify consistent markers over time. Such variability could be mistaken for noise or transient events unrelated to wormhole phenomena. Current surveys and telescopes are optimized to detect well-understood objects, stars, galaxies, black holes, neutron stars, with established signatures. The exotic, hypothesized nature of wormhole core stars demands new search strategies, data analysis algorithms, and interdisciplinary collaboration between theorists and observational astronomers to define and identify candidate objects. Another hurdle is the vast distances to potential wormhole core stars. Signals from these objects would be faint and subject to cosmic redshift, scattering, and absorption by interstellar and intergalactic matter. This attenuation challenges the detection of fine spectral features or gravitational anomalies, necessitating ultrasensitive detectors and long observation times. In the realm of gravitational waves, which offer a promising window into compact object physics, the unique waveform signatures of wormhole core stars remain largely theoretical. Current gravitational wave observatories like LIGO and Virgo are tuned to detect mergers of black holes and neutron stars, but signals from wormhole interactions, such as echoes, caused by the wormhole structure, require new data analysis techniques and may lie below present detection thresholds. Furthermore, the complex interplay between wormhole core stars and their environments can mask or mimic signals. For instance, surrounding accretion disks, stellar companions, or interstellar material can produce emissions and gravitational effects that confound attempts to isolate wormhole-specific features. Overcoming these obstacles will require advances in telescope sensitivity, gravitational wave detection, theoretical modeling, and data analysis. Upcoming missions and next-generation instruments hold promise for pushing these frontiers, but the search for wormhole core stars remains a formidable quest at the edge of human knowledge. The quest to detect wormhole core stars, those enigmatic stellar objects harboring stable wormholes at their centers, hinges critically on the advancement of astronomical instrumentation and observational strategies. Given the extraordinary subtlety and rarity of these hypothesized stars, the tools of the future must push the boundaries of sensitivity, resolution, and multi-messenger astronomy to unprecedented levels. Fortunately, the coming decades promise a new era of telescopes and space missions equipped with cutting-edge technology, poised to explore the cosmos with extraordinary precision. These instruments may finally provide the data needed to identify wormhole core stars or at least constrain their existence. One of the most promising frontiers lies in next-generation space-based observatories that cover a wide range of the electromagnetic spectrum, from infrared to high-energy X-rays and gamma rays. Unlike ground-based telescopes, space observatories avoid atmospheric interference, allowing for clearer, more precise observations of faint and distant sources, essential for detecting the weak or unusual signals expected from wormhole core stars. The James Webb Space Telescope, JWST, launched recently, provides unprecedented infrared sensitivity and resolution. While primarily designed for studying early galaxies and exoplanets, JWST's capabilities enable detailed spectroscopic analysis of compact objects and their environments. Its observations may help identify unusual spectral signatures or gravitational lensing effects suggestive of wormhole core stars, especially in dense stellar clusters or galactic centers where such objects might reside. Building on JWST's successes, proposed missions like the Origin Space Telescope, OST, and the Lynx X-ray Observatory aim to extend sensitivity further into the far-infrared and X-ray bands, respectively. The Lynx Observatory, with its high-resolution imaging and spectroscopy in the X-ray regime, is particularly relevant for wormhole core star detection. X-rays penetrate dense matter and reveal high-energy processes near compact objects, potentially distinguishing the exotic radiation environments of wormhole stars from those of neutron stars or black holes. On the high-energy frontier, next-generation gamma-ray observatories such as the Cherenkov Telescope Array (CTA) and proposed missions like the Advanced Telescope for High-Energy Astrophysics (ATHENA) will provide enhanced capabilities to detect gamma rays and hard X-rays. These instruments could capture transient or steady emissions shaped by the unique space-time curvature and exotic matter in wormhole core stars, offering clues to their presence. Beyond electromagnetic observations, the field of gravitational wave astronomy is rapidly advancing. Facilities like LIGO, Virgo, and the upcoming CAGRA have already demonstrated the ability to detect gravitational waves from black hole and neutron star mergers. However, wormhole core stars may produce distinctive gravitational wave signatures, such as echoes, caused by the wormhole's geometry or unusual oscillation modes linked to exotic matter dynamics. The proposed Laser Interferometer Space Antenna, LISA, set for launch in the 2030s, will open a new window by detecting lower-frequency gravitational waves emitted by more massive or distant systems. LISA's sensitivity could uncover signals from binary systems involving wormhole core stars or detect subtle perturbations indicative of wormhole-induced space-time distortions. In addition to individual observatories, multi-messenger astronomy, the combined study of electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays, will be vital. Coordinated observations across these channels enhance the ability to identify and characterize exotic objects like wormhole core stars. For example, a gravitational wave detection paired with unusual electromagnetic signals could provide compelling evidence for such stars. Neutrino observatories like IceCube and the upcoming Hypercameo Candy complement this approach by detecting elusive neutrinos that might originate from energetic processes near wormhole cores. Neutrino signals are less affected by intervening matter and magnetic fields, offering unique insights into extreme astrophysical environments. On the theoretical and computational side, advances in data analysis algorithms, machine learning, and simulations are crucial. Extracting subtle wormhole core star signatures from vast datasets requires sophisticated pattern recognition and anomaly detection methods. Projects developing these tools in tandem with new instruments will maximize the chances of discovery. Ground-based telescopes also contribute significantly. The upcoming Extremely Large Telescope, ELT, with its 39-meter primary mirror, will deliver unmatched optical and near-infrared resolution and sensitivity. ELT's ability to resolve fine details in crowded stellar environments can help distinguish candidate wormhole core stars by analyzing their motion, spectra, and interactions with surrounding matter. Similarly, radio astronomy arrays like the Square Kilometer Array, SKA, will provide deep, high-resolution views of the radio sky. SKA could detect unusual pulsar timing or radio emissions affected by wormhole-induced space-time anomalies, offering indirect evidence of wormhole core stars. In sum, the synergy of these future telescopes and missions, spanning the electromagnetic spectrum, gravitational waves, neutrinos, and cosmic rays, creates an unprecedented observational arsenal. Their combined capabilities bring humanity closer to detecting or ruling out the existence of wormhole core stars. However, challenges remain. Identifying unambiguous signatures of wormhole core stars demands not only technological advancement, but also refined theoretical models to predict what to look for. Close collaboration between theorists and observers will be essential in guiding targeted searches and interpreting anomalous data. As these new instruments come online over the next decades, the quest to find wormhole core stars exemplifies the frontiers of astrophysical discovery. Whether confirming these stars exist or constraining their nature, these missions promise to deepen our understanding of the universe's most extreme phenomena and the fundamental structure of spacetime itself. Confirming the existence of wormhole core stars would mark a profound turning point in the trajectory of physics and cosmology, fundamentally reshaping our understanding of the universe's architecture, the nature of spacetime, and the foundational laws that govern reality itself. These stars, hypothesized to naturally contain stable wormholes at their centers, would bridge the gap between abstract theoretical constructs and tangible astrophysical phenomena, offering empirical validation of concepts that have long remained in the realm of speculation. Central to this transformative impact is the challenge wormhole core stars pose to the classical notion of spacetime as a smooth, continuous fabric. According to Einstein's general theory of relativity, gravity is not a force acting at a distance but a manifestation of curved spacetime geometry shaped by matter and energy. Wormholes, as theoretical solutions to Einstein's field equations, represent non-trivial topologies, essentially tunnels or bridges linking disparate points in spacetime, potentially across vast cosmic distances or even different universes. While the mathematics permit their existence, the stability of such wormholes requires the presence of exotic matter with negative energy density, a form of matter that counteracts the gravitational forces tending to pinch these tunnels shut. The discovery of wormhole core stars would provide the first direct evidence that such exotic spacetime configurations are not just mathematical artifacts but genuine astrophysical objects. This would revolutionize our conceptual framework, suggesting that the universe's fabric is interlaced with complex connectivity far beyond the simple, smooth models traditionally used in cosmology. It implies that the cosmos might resemble a vast network of interconnected nodes, where wormholes act as shortcuts linking regions that otherwise seem causally disconnected. A fundamental implication of this discovery is the validation of exotic matter as a real physical entity. Exotic matter, characterized by negative energy density and the violation of classical energy conditions, has long been theorized but never empirically observed. Its existence challenges deeply held assumptions in both classical and quantum physics. Exotic matter's repulsive gravitational effect is precisely what would keep wormholes stable and traversable, preventing their natural collapse. If wormhole core stars harbor this substance, it opens the door to new physics beyond the standard model, possibly reshaping particle physics and quantum field theory to include these unconventional forms of matter energy. The presence of exotic matter within wormhole stars could also shed light on some of the most enigmatic components of our universe: dark matter and dark energy. These two mysterious phenomena comprise about 95% of the universe's total energy budget, yet their true nature remains elusive. Dark energy drives the accelerated expansion of the universe, while dark matter exerts gravitational effects that influence galaxy formation and rotation. Understanding exotic matter's properties and behavior might offer a unified explanation for these cosmic puzzles. It's conceivable that the exotic matter stabilizing wormholes contributes to or interacts with dark energy, or dark matter, providing a link between microphysical phenomena and large-scale cosmic evolution. On the frontiers of theoretical physics, the confirmation of wormhole core stars would greatly advance the pursuit of a quantum theory of gravity, the long-sought framework that unites general relativity with quantum mechanics. Wormholes inhabit the regime where the smooth geometry of spacetime and the discrete, probabilistic nature of quantum phenomena intersect. Empirical observations of wormhole core stars would allow scientists to test predictions of quantum gravity models, such as string theory or loop quantum gravity, under real astrophysical conditions. This data would provide invaluable constraints and guidance for developing a coherent and predictive theory that governs the behavior of spacetime and matter at the Planck scale. From a cosmological perspective, wormhole core stars would force a radical revision of our understanding of the universe's large-scale structure and evolution. Traditionally, cosmology relies on the cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales, appearing roughly the same from any vantage point. The introduction of stable wormholes into this framework suggests a universe with a more intricate global topology, where distant regions are linked by natural space-time tunnels. This could help explain phenomena such as the horizon problem, which questions how widely separated regions of the universe exhibit nearly identical properties despite the limits imposed by the speed of light. Wormholes may provide causal pathways enabling information and energy exchange across vast distances, thereby contributing to observed uniformities without requiring inflation alone. Additionally, wormhole core stars could account for certain puzzling astrophysical phenomena that currently defy conventional explanation. For example, fast radio bursts, FRBs, intense, millisecond-long pulses of radio waves originating from distant galaxies, remain a mystery. The unique gravitational and electromagnetic environment near wormhole cores might produce or modulate such signals, offering a novel source mechanism. Similarly, gravitational wave signals exhibiting unexpected echoes or anomalies could arise from matter interacting with wormhole structures, providing indirect evidence of their presence. The implications extend beyond physics and cosmology into the realm of philosophy and metaphysics. Wormholes, particularly if stable and traversable, allow for the theoretical possibility of closed time-like curves, paths through space-time that loop back to earlier times, permitting time travel and potential causality violations. This challenges our conventional understanding of cause and effect and raises profound questions about determinism, free will, and the nature of time itself. Observational confirmation of wormhole core stars would force a re-examination of these concepts and might necessitate new physical principles or reinterpretations to resolve paradoxes inherent in time travel scenarios. Furthermore, wormhole core stars provide compelling empirical support for multiverse theories. The idea that our universe is just one of many, potentially with different physical laws and constants. If wormholes connect separate universes, then these stars could be cosmic portals linking alternate realities, making the multiverse more than a speculative notion but a physically testable hypothesis. This would fundamentally broaden our conception of reality, challenging the uniqueness of our universe and inviting exploration of its neighbors through astronomical observation. The discovery of wormhole core stars would also have transformative technological implications, albeit likely far in the future. Harnessing stable wormholes for travel or communication could revolutionize humanity's capacity to explore space, effectively bypassing the enormous distances and timescales involved in interstellar or even interuniversal voyages. Instantaneous transmission of information or matter through wormholes would revolutionize communication and transportation technologies, potentially opening pathways to new energy sources derived from exotic matter or space-time manipulation. Yet, these prospects also raise complex practical and ethical questions. The stability of wormholes, potential hazards associated with traversing or interacting with them, and their impact on causality and the broader universe would necessitate careful scientific and philosophical consideration. The ability to manipulate such profound aspects of reality could have unintended consequences, demanding responsible stewardship. In sum, the confirmation of wormhole core stars would upend centuries of scientific thought, reshaping physics, cosmology, and philosophy. It would unveil a universe far richer and more interconnected than previously imagined, where exotic matter and space-time tunnels play fundamental roles in cosmic evolution. This discovery would not only deepen our scientific understanding but expand humanity's cosmic horizon, inspiring new generations to explore the mysteries that lie beyond. The concept of wormhole core stars inevitably leads us to one of the most tantalizing and profound ideas in modern theoretical physics: the multiverse. The multiverse hypothesis posits that our universe is just one of many, potentially an infinite number, each with its own distinct physical laws, constants, and histories. While this idea has long been debated within philosophical and scientific circles, wormhole core stars offer a concrete, astrophysical framework that could bridge the gap between speculative multiverse theory and observable phenomena. At its essence, a wormhole is a tunnel through spacetime that connects two separate regions. If the ends of such a tunnel lie not just in distant parts of our universe but in entirely different universes, wormholes become cosmic bridges between distinct realms of reality. Wormhole core stars, stars harboring stable wormholes at their centers, could thus function as natural gateways or portals linking our universe to these parallel or alternate universes. This concept elevates the multiverse from an abstract theoretical construct to something that might, in principle, be physically accessed or at least detected. This connection between wormhole stars and the multiverse rests on several pillars of theoretical physics. Quantum cosmology and string theory often predict a landscape of possible vacuum states or universes, each representing a different set of physical parameters. The idea that these universes might coexist in a higher dimensional, multiverse, framework is well established in certain models. However, direct interaction or travel between these universes has seemed nearly impossible within conventional frameworks. Wormholes, stabilized by exotic matter, provide a mechanism by which these different universes could be connected. If wormhole core stars exist, they may embody these connections, serving as nodes where the fabric of multiple universes intersect. This opens the possibility that matter, energy, or information could traverse between universes through these stellar gateways, albeit with immense physical challenges. From a cosmological perspective, this could have fascinating implications. For example, certain unexplained cosmic signals, such as unusual bursts of radiation, anomalous gravitational wave patterns, or even some instances of fast radio bursts, might originate from interactions involving wormholes connecting different universes. Moreover, the existence of such stars could provide empirical avenues to test multiverse theories. Currently, the multiverse remains largely untestable because the other universes are causally disconnected from ours, making direct observation impossible. However, if wormhole core stars act as bridges, they could produce detectable signatures, unusual gravitational lensing effects, characteristic distortions in light spectra, or exotic particle emissions that would indirectly signal interactions beyond our universe. This concept also influences our philosophical understanding of existence and reality. The possibility of stable wormhole gateways suggests that the boundaries between universes are permeable, challenging the notion that our universe is an isolated, cosmic island. Instead, reality may be a vast interconnected web of universes, each influencing and communicating with others through these exotic stellar portals. This vision elevates the multiverse from metaphysical speculation to a physical reality intertwined with our own cosmos. Additionally, this connection sheds light on the origin and fate of our universe. Some cosmological models propose that universes can bud off from parent universes or collide with each other in a higher dimensional space. Wormhole core stars could be remnants or relics of such cosmic events, representing points where universes merge or exchange matter and energy. This could help explain the fine-tuning of physical constants, or the apparent initial conditions of our universe, influenced by multiversal interactions transmitted through these stellar wormholes. From a theoretical standpoint, this connection aligns with developments in string theory and quantum gravity, where extra dimensions and complex topologies naturally arise. Wormholes embedded in stars could be manifestations of higher dimensional structures, connecting branes or bulk spaces that host multiple universes. These frameworks suggest that the multiverse is not just an abstract possibility, but a structural feature of the cosmos, with wormhole core stars as its physical anchors. The practical implications of this connection, while speculative, are profound. If stable wormholes linking universes exist and could be understood or manipulated, they might enable forms of interuniversal travel, communication, or even exchange of matter and information. Such capabilities would revolutionize physics, cosmology, and potentially the destiny of intelligent civilizations, vastly expanding the scope of exploration and understanding beyond our own universe. However, this vision also raises profound questions and challenges. The stability and safety of traversing wormholes, the physical laws governing interuniversal travel, and the potential consequences of interacting with other universes, ranging from cosmological disruptions to philosophical dilemmas about identity and causality, would demand careful scientific and ethical scrutiny. In summary, wormhole core stars serve as a conceptual and potentially observational bridge between our universe and the multiverse. Their existence would transform the multiverse from a speculative idea into a testable, physical framework where multiple universes are interconnected through natural cosmic gateways. This paradigm shift would deepen our understanding of reality's vastness and complexity, inviting us to reconsider our place within a potentially infinite, interconnected cosmic landscape. The enigmatic nature of dark matter has perplexed astronomers and physicists for decades. Accounting for roughly 27% of the universe's total mass energy content, dark matter exerts a gravitational influence that shapes galaxy formation, governs cosmic structure, and affects the dynamics of clusters, yet it remains invisible and elusive to direct detection. Its fundamental composition and properties remain some of the greatest mysteries of modern science. Intriguingly, wormhole core stars, a hypothetical class of stars harboring stable wormholes at their centers, may offer a fresh lens through which to explore this cosmic puzzle, suggesting potential interactions or deep connections between these exotic stellar objects and dark matter. To understand this possible connection, it helps first to consider the unique nature of wormhole core stars. These stars, unlike ordinary stars, are theorized to contain stable wormholes maintained by exotic matter with negative energy density, defying the normal rules governing known particles and energy forms. The gravitational environment around such a star would be radically different, featuring intense warping of spacetime and possibly exotic fields or particles associated with the wormhole's stability. Given that dark matter's primary evidence comes from its gravitational effects rather than electromagnetic emissions, wormhole core stars might influence, or be influenced by dark matter in several fascinating ways. One speculative possibility is that wormhole core stars serve as natural accumulation points, or traps, for dark matter particles. Since dark matter interacts primarily through gravity, these stars' unusual gravitational profiles, marked by intense curvature and potentially unique spacetime geometries, might attract or concentrate dark matter particles more effectively than normal stars. This could lead to higher local dark matter densities near wormhole core stars, influencing their dynamics and evolution. Such concentrations might produce indirect signals, such as enhanced annihilation events if dark matter consists of weakly interacting massive particles, WIMPs, leading to gamma-ray emissions or other high-energy phenomena detectable by sensitive instruments. Another avenue of interaction could stem from the exotic matter stabilizing the wormhole itself. While exotic matter is distinct from dark matter in current theoretical frameworks, it's conceivable that some dark matter candidates, particularly those involving unknown fields or particles beyond the standard model, might possess exotic properties aligning with or influencing the negative energy densities required for wormhole stability. If so, wormhole core stars might form in regions rich in such exotic dark matter, or the presence of wormholes might catalyze processes that convert ordinary dark matter into exotic states. This interplay would blur the distinctions between exotic matter and dark matter, suggesting a unified framework that addresses multiple cosmic mysteries simultaneously. Moreover, wormhole core stars could act as natural laboratories for probing dark matter's properties. The unique spacetime environment near these stars might affect dark matter particle behavior, such as altering annihilation cross-sections, decay rates, or interaction probabilities. Observing phenomena near wormhole core stars, such as unusual radiation signatures, gravitational lensing anomalies, or deviations in stellar motion, could provide indirect but critical clues about dark matter's nature. For example, unexplained excesses of high-energy photons or neutrinos near suspected wormhole stars might hint at dark matter interactions modified by the wormhole's exotic environment. Additionally, if wormholes connect distant parts of our universe or even different universes, they might serve as conduits for dark matter transfer or redistribution on cosmological scales. This could influence the large-scale structure of dark matter halos enveloping galaxies and clusters, potentially explaining anomalies in their distribution or dynamics. Wormhole-mediated flows of dark matter could help reconcile discrepancies between simulations of structure formation and observed galactic rotation curves or cluster behavior. From a theoretical standpoint, some models in quantum gravity and string theory propose that dark matter and exotic matter arise from related fundamental fields or brane configurations. In these contexts, wormhole core stars may embody regions where these fields manifest intensely, intertwining the phenomena of wormholes and dark matter. This suggests that discovering and studying wormhole core stars could be pivotal not only for understanding spacetime geometry but also for uncovering the microphysical nature of dark matter. Despite the speculative nature of these ideas, the potential link between wormhole core stars and dark matter invigorates efforts to search for indirect signatures. Observatories targeting gamma rays, cosmic rays, neutrinos, and gravitational waves could look for anomalies consistent with wormhole-induced dark matter effects. Likewise, detailed mapping of dark matter distributions in galaxies and clusters might reveal unexpected correlations with exotic stellar objects, hinting at the presence of wormhole stars. In conclusion, While much remains theoretical, the possible connections between wormhole core stars and dark matter open exciting new frontiers in understanding the cosmos. Wormhole stars may influence dark matter distribution, serve as sites of exotic matter-dark matter interplay, or act as cosmic beacons revealing dark matter's elusive properties. Exploring these intersections deepens our quest to unravel the universe's hidden fabric and the mysterious matter shaping its destiny. Fast radio bursts, FRBs, are among the most enigmatic and captivating phenomena in modern astrophysics. First discovered in 2007, these incredibly brief but intensely powerful pulses of radio waves, lasting only milliseconds, originate from distant galaxies billions of light-years away. Despite extensive observation and study, the origins of FRBs remain largely mysterious, with theories ranging from magnet-Rs and neutron stars to exotic phenomena involving black holes or even advanced extraterrestrial technologies. Among these hypotheses, wormhole core stars present a fascinating and novel potential explanation, merging exotic astrophysics with cosmic signals that challenge conventional understanding. The core challenge in explaining FRBs lies in their defining features: their transient, extremely high-energy nature, immense luminosity, and in many cases, apparent randomness. They emit as much energy in a few milliseconds as the Sun does in a few days, but their precise sources have eluded definitive identification. Traditional candidates like magnet-Rs, highly magnetized neutron stars, have had some success explaining repeating FRBs, yet many bursts exhibit characteristics that remain puzzling, such as non-repeating single events, complex temporal structures, and unusual frequency behaviors. Wormhole core stars, theoretical stellar objects hypothesized to contain stable wormholes at their centers, offer a compelling new avenue for interpreting these signals. The intense gravitational fields, exotic matter presence, and unique space-time topologies near such stars could generate or modulate electromagnetic radiation in ways that produce the observed properties of FRBs. One speculative mechanism involves the dynamics of matter interacting with the wormhole's throat. As matter, such as stellar wind, gas clouds, or debris, falls toward the wormhole core, it would experience extreme tidal forces, space-time distortions, and acceleration. These interactions could induce bursts of radiation, particularly in the radio spectrum, as charged particles spiral along magnetic field lines or undergo sudden energy releases due to magnetic reconnection events amplified by the wormhole's exotic environment. The highly localized and transient nature of such interactions aligns well with the millisecond timescales of FRBs. Furthermore, wormhole cores might act as natural amplifiers or modulators of incoming electromagnetic signals. Radiation traveling through or near the wormhole could be gravitationally lensed, blue-shifted, or scattered in complex patterns, producing the sharp, intense bursts detected on Earth. Variations in wormhole stability or surrounding matter densities might cause the intermittent and irregular repetition patterns seen in some FRBs. Another intriguing possibility arises from the quantum properties of the exotic matter stabilizing the wormhole. Fluctuations or instabilities in this matter could trigger sudden energy releases, analogous to quantum tunneling or vacuum decay events, producing powerful electromagnetic pulses. These quantum phenomena might manifest as bursts with distinctive signatures, potentially explaining some of the unusual frequency drifts or polarization behaviors observed in FRBs. Wormhole core stars could also explain FRBs that appear to originate from distant, seemingly isolated regions with no obvious host galaxies or conventional stellar counterparts. If wormholes connect disparate regions of space, or even different universes, radiation emitted or modulated by matter passing through these cosmic tunnels might emerge far from their point of origin. This could produce bursts seemingly out of place, relative to known astrophysical environments, aligning with observations of FRBs in unexpected locales. Observationally, identifying wormhole core stars as FRB sources would require detecting correlated signatures beyond radio bursts. For example, gravitational wave observatories might capture unique waveforms associated with matter dynamics near wormholes. X-ray or gamma-ray telescopes could detect high-energy counterparts to radio bursts, while precise timing and polarization measurements might reveal distinctive modulations imparted by wormhole-induced spacetime curvature. Moreover, repeated bursts from the same source, exhibiting complex temporal patterns or frequency drifts, could reflect changes in wormhole conditions or matter inflow rates. Monitoring these variations might provide insights into wormhole stability and the exotic physics governing these stars. While wormhole core stars remain hypothetical, their potential role in explaining FRBs invigorates the search for new observational evidence. Upcoming radio telescope arrays, such as the Square Kilometer Array, SKA, and upgrades to existing facilities, promise increased sensitivity and resolution, enhancing our ability to characterize FRB sources and discriminate between competing models. In summary, wormhole core stars offer a rich and imaginative framework for understanding fast radio bursts, integrating extreme astrophysics, exotic matter physics, and space-time geometry into a coherent scenario. By considering these exotic stars as natural cosmic broadcasters or modulators of FRBs, scientists gain a novel perspective on one of the universe's most perplexing signals, driving further exploration at the intersection of theory and observation. The discovery of a naturally stable wormhole inside a star would ignite humanity's imagination, but it would also force us to face an overwhelming list of ethical concerns before taking the first step through it. On the surface, the prospect of instant travel to distant galaxies or even other universes sounds like an unparalleled opportunity. But beneath the wonder lies a tangled web of moral considerations, many of which have no precedent in human history. If a wormhole can connect our reality to another place or time, then every decision about using it carries consequences that could be irreversible. One of the first dilemmas is ownership. Who would control access to such a portal? If it's discovered in deep space, does it belong to the organization or nation that finds it first, or should it be considered the collective property of humanity, or perhaps of all intelligent beings that exist? The stakes are infinitely higher than with ordinary natural resources. Unlike oil fields or mineral deposits, a wormhole is not just a resource, it's a gateway, a potential lifeline, or a weapon. If controlled by a small group, it could shift the balance of power across the planet, giving them unprecedented control over trade, exploration, and even survival. Yet making it open to everyone invites chaos and misuse. This leads to the unavoidable ethical question: is it better to restrict access for safety, or allow universal access for fairness? The second concern is the impact on the place on the other side. In our history, whenever a technologically advanced culture encounters a less advanced one, the result is often exploitation, cultural erosion, or outright destruction of the weaker society. If a wormhole leads to a world inhabited by intelligent life, rushing in uninvited could repeat the worst mistakes of our past on a cosmic scale. Even if the inhabitants are technologically equal or superior, our arrival could disrupt their balance in ways we can't foresee. Ethically, we must ask whether we even have the right to set foot there without explicit consent. The situation becomes even more complex if the other side is uninhabited but contains valuable resources. Would extracting those resources be harmless? Or would it be another form of interdimensional colonialism? There is also the question of environmental ethics. Passing through a wormhole isn't like walking into another country, it's traversing space-time itself. We don't fully understand whether our travel could destabilize the wormhole, alter the environment on the other side, or cause unforeseen ripple effects in both locations. Even the act of sending probes could unintentionally contaminate alien ecosystems, introducing bacteria, chemical residues, or radiation. History has shown us how introducing even a single invasive species to a fragile ecosystem can cause irreparable harm. On an interstellar or interuniversal scale, the stakes are magnified beyond comprehension. Do we have an ethical obligation to leave the other side completely untouched until we can guarantee safety? And what if that guarantee is impossible? The wormhole could also pose existential threats. If it connects our universe to another, we can't predict the physical laws or dangers we might encounter. It could be stable now, but what if using it creates strain that leads to collapse or catastrophic energy release? More disturbingly, what if using it invites unwanted attention? Any civilization advanced enough to notice our arrival might not respond with curiosity. They might see us as a threat. Ethical reasoning demands that we consider the potential to endanger not just ourselves, but the entire planet. This raises the haunting question: is any potential gain worth even a small chance of total annihilation? Beyond safety, there's the moral issue of inequality. If wormhole travel becomes possible, who gets to use it first? Would it be scientists, or the wealthy elite? History suggests that access to transformative technologies rarely begins with equality in mind. Allowing only certain people to explore or settle on new worlds could deepen global inequality, creating a new form of class divide: those who can step across the stars and those who are forever earthbound. On the other hand, making it freely available without regulation could spark mass migration, resource competition, and possibly interdimensional conflict. The ethics of distribution might be even harder to solve than the physics. There is also the philosophical dimension of identity and belonging. If wormholes allow us to reach universes with different histories, different versions of Earth, or even alternate versions of ourselves, what ethical rules govern interaction? Would meeting an alternate version of you be harmless curiosity, or a violation of that person's autonomy? Could it cause psychological damage to either party? And if one version of Earth is in crisis, facing famine, war, or extinction, would it be ethical to allow migration from that Earth to ours, or vice versa? Helping could be noble, but it could also destabilize both worlds. The potential for exploitation or displacement is immense. Even in the absence of life on the other side, time becomes an ethical problem. Wormholes might connect not just to different places, but to different points in time. Traveling into the past could create paradoxes, but even traveling to the future raises questions. Would we have the right to bring back knowledge of events yet to occur? Could we ethically use that knowledge for profit? Some might argue that simply knowing the future would alter it in ways that violate the natural course of events. Others might argue that not using such knowledge to prevent disasters would be morally wrong. Both positions have merit, and both reveal the same truth. Wormhole travel blurs the lines between exploration, interference, and manipulation. Security is another pressing concern. A wormhole portal could be weaponized in ways humanity has never imagined. It might serve as an instant pathway for moving troops, weapons, or even dangerous materials into strategic locations. Worse, it could be used to bring hostile forces directly to our doorstep. If we can travel through it, so can others. The ethical question becomes one of mutual vulnerability. Do we have a right to close a wormhole to protect ourselves, even if it cuts off access for peaceful explorers on the other side? The ethical challenges extend to our very definition of responsibility. Suppose we encounter intelligent life that is suffering, whether from natural disasters, disease, or war. Do we have a moral obligation to help them, or should we avoid involvement entirely? Intervention could save lives, but it could also cause cultural dependency or provoke unintended consequences. Choosing not to act might preserve their autonomy, but it might also condemn them to suffering we could have prevented. This is a version of the classic moral dilemma. If you can save someone without harming yourself, are you obligated to do so? In the context of wormholes, the scale and complexity of that question are unprecedented. Even the act of observation raises moral issues. Using a wormhole to spy on other civilizations, whether to study them or assess their potential threat, could be considered a violation of privacy. Our own history contains countless examples of surveillance leading to mistrust and conflict. If the roles were reversed and another civilization began observing us without permission, most would consider it a hostile act. Finally, there is the most profound ethical question of all: should we use it at all? The temptation to explore, to push boundaries, is deeply human. But curiosity has always been balanced by caution, or at least it should be. Some philosophers might argue that certain doors are best left closed, not because we fear what's behind them, but because opening them might forever change who we are. The moment we step through a wormhole, humanity ceases to be a purely earthbound species. We become something else, something larger, but also something more entangled with forces and fates we can't yet understand. The ethical weight of that transformation cannot be overstated. In the end, the decision to use a wormhole portal would not be made by scientists alone. It would require the combined wisdom of physicists, ethicists, diplomats, philosophers, and perhaps even theologians. The questions it raises, about ownership, consent, safety, equality, responsibility, and identity, are as vast as the portal itself. We may dream of walking among the stars or stepping into parallel worlds, but before we do, we must first ask ourselves not just if we can, but if we should. The universe may not give us a second chance to get the answer right. If a wormhole core star were to appear near Earth, the event would represent one of the most profound and potentially dangerous moments in human history. Such a star, with its natural and stable wormhole embedded at its core, is not merely another stellar object to catalog. It is a cosmic anomaly that could reshape our understanding of physics, space travel, and the very boundaries of reality. But before we could even begin to think about exploration, we would have to confront the immediate consequences of such an arrival, both physical and societal. The first question is proximity. Near, in astronomical terms, might still mean millions of kilometers away, yet even that distance could bring dramatic effects. The gravitational presence of a wormhole core star would depend on its mass and its nature. If it had a mass similar to our Sun, but appeared suddenly within our solar system, the delicate gravitational dance of planets, moons, and asteroids could be disrupted. Orbits might shift subtly or catastrophically, depending on where the star manifested. Earth's orbit could stretch or compress, altering our seasons, climate stability, and even the length of our year. If the new star's gravitational pull combined with the Sun's in certain ways, it could fling smaller objects, asteroids and comets, into unpredictable new trajectories, potentially increasing the likelihood of impacts. In the worst-case scenario, our planet's orbit could destabilize entirely, sending us on a collision course with another world or hurling us into the cold darkness of interstellar space. But beyond gravity, the wormhole itself poses unique and unpredictable dangers. A stable wormhole is, by definition, a pathway connecting two distant points in spacetime, possibly in entirely different universes. If the other side opened into a region of intense radiation, a black hole's accretion disk, or even the core of another star, energy and matter could begin to flow into our region of space. Streams of high-energy particles could pour through, creating dangerous radiation belts or heating the surrounding space to extreme levels. Depending on the wormhole's stability and size, this could be as minor as a new aurora in our skies, or as devastating as an atmosphere-stripping wave of gamma rays that sterilizes the surface of Earth. If the other end of the wormhole opened into a vacuum of deep space, the effects might be gentler, but there would still be dangers. A pressure imbalance between our side and the other could cause matter to be sucked in or spewed out. If even a small amount of interstellar gas began funneling through, the flow could generate electromagnetic fields, shockwaves, and unpredictable stellar winds. If large objects, asteroids, debris, or even alien spacecraft were to drift through, we could suddenly find ourselves sharing the solar system with foreign matter, technology, or even life forms from far beyond our galaxy. The sudden appearance of such a star would immediately become the single most studied object in human history. Every telescope, probe, and space observatory would turn toward it, measuring gravitational effects, scanning for radiation signatures, and mapping its wormhole mouth. Governments would scramble to decide how to respond, while the public would be split between wonder and terror. The idea that another universe, or at least another corner of our own, was just a short distance away could inspire dreams of exploration, colonization, and limitless resources. But at the same time, it could provoke fears of invasion, contamination, or cosmic catastrophe. If the wormhole connected to a location inhabited by intelligent life, the stakes would multiply. The appearance of the star might not be an accident, it could be deliberate, perhaps even a form of contact initiated by a civilization far more advanced than ours. If they had the power to move a wormhole core star into position, they would be operating on a scale of engineering we can barely imagine. Would they be offering a gift, or setting a trap? Would we even be able to communicate before events began to spiral beyond our control? The energy output of a wormhole core star could also alter our technological landscape overnight. If stable and safe, it might provide a limitless source of power. We could, in theory, tap into the gravitational, electromagnetic, or even direct energy transfer properties of the wormhole to fuel spacecraft, supply entire planets, or power weapons of unimaginable scale. But with such potential comes risk. If any nation, corporation, or group gained exclusive control over it, they could dominate the Earth and possibly extend that dominance far beyond. Another unsettling possibility is that the star's wormhole could act not just as a passageway, but as a kind of gravitational sink. If its other mouth lay in a region of stronger gravity, objects, ships, probes, even entire planets, could be drawn in without warning. Over time, our solar system might lose mass, perhaps slowly at first, then accelerating as the wormhole's influence grows. In the most extreme outcome, even the sun itself could eventually be consumed, leaving Earth adrift in the cold void. The psychological strain of knowing a cosmic gateway hangs in our skies could be immense. Entire populations might live in fear of what could come through, or of the wormhole destabilizing and causing a catastrophic collapse. Scientists would warn of unknown physics. Could the wormhole destabilize local space-time? Could it trigger a chain reaction leading to the destruction of our solar system? No one could be entirely certain, and that uncertainty might be as dangerous as any physical threat. If humanity acted cautiously, we might attempt to send probes through the wormhole before risking human explorers. But those probes might never return, or might return altered in ways we cannot predict. The wormhole could distort time. What we send in today could emerge thousands of years in the past or future on the other side. Or, in the most disorienting twist, we might send something in and receive it back instantly, only to discover it had aged millennia in transit. Such time distortions could make the wormhole not just a portal through space, but a potentially dangerous bridge through history itself. Ultimately, the arrival of a wormhole core star near Earth would be a moment of both supreme opportunity and existential peril. It could open the door to interstellar exploration without the need for faster-than-light travel, potentially making us a multi-universal civilization in a single leap. But it could just as easily bring hazards beyond our ability to control, alien threats, cosmic disasters, and physics we do not yet understand. Humanity's reaction would define the outcome, whether we approached it with unity, caution, and wisdom, or with fear, competition, and short-term ambition. In many ways, the appearance of such a star would be a test, not just of our technology or our science, but of our maturity as a species. And in that test, the stakes could not be higher. If wormhole core stars exist, they would stand as some of the most extraordinary and awe-inspiring phenomena in the entire cosmos, a fusion of two of nature's most profound mysteries, the power of stars and the theoretical elegance of wormholes. They would not just be objects of scientific curiosity, they would be gateways, potential bridges to distant realms that lie beyond our current reach. In a universe where even the fastest spacecraft would take tens of thousands of years to cross to the nearest stars, the idea of a shortcut, a cosmic expressway, feels almost like science fiction brought to life. Yet, in contemplating these stars, we are forced to consider that the universe may hold possibilities far stranger than fiction could ever invent. The very notion of a wormhole core star reshapes our understanding of what a star could be. Traditionally, stars are immense spheres of plasma, nuclear furnaces sustained by the balance between gravitational collapse and fusion pressure. But in this hypothetical scenario, a star could also be something much more, a natural machine capable of bending spacetime itself. Instead of simply radiating energy outward, it could serve as a focal point for gravitational warping so intense and stable that it forms a permanent tunnel to another location. Such a concept challenges not only astrophysics but also philosophy, raising the question of whether the universe itself contains an architecture for travel that transcends the limitations of light speed. If such a star could be navigated safely, it could transform our place in the cosmos overnight. Humanity could leapfrog across thousands, or even millions of light years instantly. Entire galaxies that would otherwise remain forever out of reach could suddenly become accessible. Civilizations that may have arisen long before ours, and perhaps achieved feats we can hardly imagine, could be visited, observed, and even befriended. In this light, a wormhole core star would not just be a cosmic curiosity. It would be a bridge to other chapters of the universe's story, chapters that until now have been closed to us. But this potential comes with profound uncertainty. The same bridge that allows us to step into distant space could open pathways from elsewhere into our own region of the universe. And we have no guarantee about what, or who, might cross in the opposite direction. In our eagerness to explore, we could unknowingly invite forces or entities whose intentions are not aligned with our survival. The concept of a wormhole is not inherently benevolent. It is merely a tool of spacetime, indifferent to the hopes or fears of those who use it. This realization adds a note of caution to the otherwise exhilarating vision of a galaxy made accessible. There's also the question of whether traveling through such a portal would even be survivable. Even if the wormhole remained stable over astronomical timescales, a requirement in our scenario, the forces inside could be extreme. Exotic matter or unknown physical effects could exist within, conditions that no spacecraft or living being could endure. Moreover, the other side of the wormhole might not be in a safe or hospitable environment. It could open in the heart of another star, inside a black hole's event horizon, or in a region of space filled with lethal radiation. In this way, a wormhole core star could be as much a trap as it is a gateway. Still, for all these uncertainties, the human imagination cannot help but dwell on the possibilities. Perhaps there is a universe where advanced civilizations have already mapped a network of such stars, using them as a cosmic transportation grid. Perhaps wormhole core stars are so rare that they exist only once in every billion galaxies, making them priceless treasures of cosmic geography. Or perhaps the first one we discover will be right on our doorstep, a sudden and unexplainable gift, or curse, from the deeper layers of reality. In the grander scheme, these stars would not just expand our physical horizons but also deepen our existential questions. What does it mean if the universe is interconnected by hidden shortcuts? Does this imply a kind of cosmic design, intentional or otherwise? Are wormhole core stars remnants of an ancient engineering project by beings who have long since vanished, leaving behind a kind of galactic infrastructure for others to stumble upon? Or are they purely natural, born from the chaotic physics of a young universe, accidental wonders with no purpose beyond what we assign to them? If we ever find one, it could become the focal point of the greatest debate in human history. Should we use it? The decision would not just be about exploration, it would be about defining the next chapter of human existence. Entering a wormhole could be a point of no return, an irreversible step into the unknown. And yet, if we refuse, we might forever wonder what wonders, or warnings, lay just beyond its threshold. The temptation to know might be irresistible, even if the risks are catastrophic. There is a poetic symmetry in imagining that the universe itself contains doors. In our daily lives, doors are transitions, ways to move from one space to another. They symbolize choice, change, and possibility. A wormhole core star would be the ultimate door, one that could swing open to reveal worlds untouched by human eyes, or perhaps realities so alien that they defy comprehension. Whether it would lead to discovery or destruction is something we cannot know until it is too late. Perhaps that is the real essence of the wormhole core star's mystery. It embodies both hope and fear in equal measure. It reminds us that the universe is not a static backdrop but an evolving, dynamic, and still largely undiscovered expanse. It is a stage with hidden trapdoors and unexpected exits, and we are merely beginning to understand the script. Whether such a star exists or not, the idea forces us to confront the scale of what we do not yet know, and the scale of what we might someday dare to try. And so, the wormhole core star stands in our imagination as the ultimate cosmic gateway, a symbol of humanity's boundless curiosity and the inherent gamble of seeking knowledge. It is the promise of connection across the vastness of space, the lure of unseen lands and unimagined wonders, and the shadow of dangers we cannot yet define. If one were to appear in our skies tomorrow, it would not just be an astronomical discovery. It would be the start of a story whose ending no one could predict. Until then, it exists in the realm of thought experiments, speculation, and dreams, reminding us that in a universe as ancient and immense as ours, there is always the chance that reality still has surprises far beyond our wildest imagining. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.